Hello, hello. Is it on? Hello. Hello, hello. It's better now? Okay? No, not. Hello. Yeah, if it's. Hello, hello. Okay. Good morning. This is the fourth day of the workshop, and our seventh lecture is on IoT data analytics. IoT data analytics is a pretty vast subject, mostly developed in recent days. And in 1 hour, if you want to do something, I would rather introduce it properly and tell the scope. And it's beyond our possibility that we cannot go to every techniques and show how it's working. With that, let's go to the starting why all this data analytics is necessary. This tells us the annual data generation today in 2025 is about 175 zettabytes. Okay? And this data includes both textual content, both structure, semi-structure, unstructured data, multimedia data like images, video, audio, and also social media data, including the data coming from sensors. If you look, almost half of the data resides in public cloud environment. That means cloud has been so popular. Half of the data storage in cloud, and 1/3 of data worldwide are needing real-time processing. Okay? And quite often they're at the edge for IoT perspective. So where do we get this data from? This data coming from many sources. As you notice here, is email, contracts, weather, population, sentiment, industry, and so many areas, both commercial, public, as we spoke in the last slide. Now, the state of ever-growing data can be believed or perceived like this. Can you believe that as we speak, last 1 minute, perhaps 204 million emails has been sent, 61,000 hours of music being listened in one of the platforms, Pandora, and 30 million photos have been viewed by the user, and it's growing much faster. Perhaps 350,000 tweets have been there in the last 1 minute. Imagine 4 million views, 277,000 Facebook logins. There are statistics taken by the surveys, and 6.3 million Google searches. So data is generated such a fast pace. So we can only measure them the volume, velocity, how quickly they are being coming off, the variety of data, and accurate or inaccurate data over there. Now, to give a perspective about how much is zettabyte, we are all used to have terabytes. That is 2 to the power, that's 1 trillion bytes, which is 2 to the power 40 bytes. Okay? Petabyte is 2 to the power 50 bytes. And zettabyte is 2 to the power 70 bytes. Okay? The amount of data consumed by US households in 2008 is 3.6 zettabytes. Okay? So this is kind of speaks the volume of data that we are getting ourselves in. Then the massive streaming data, more so as the data is cheaper for you and you love to send videos, watch videos, they're all part of the streaming data, and essentially we call that data with velocity. Okay? Then variety of data, so many sources, unstructured or semi-structured, all these things coming from social media, sensors, and for us it is more or less sensor and media, and the variety is changing over and over again. Think about 4 billion plus data hours of video, they're all around there. Tweets, okay? Now, variety of data is changing, you're getting more and more varieties every day, but we are not sure that the data we generate or data being stored, data being used, how accurate they are. So veracity means data accuracy, or in other words, data uncertainty. Okay? So this is a challenge, that data being looked at, data being sent for analysis, unless they are accurate, you are not going to get accurate answers. Good data can give you good answers, and with data to uncertainty is a pain. Now, as regards to data, from IoT in particular, what are the challenges? That's some of the prominent challenges have been noted here, such as multimodal data and coming from heterogeneous devices. We'll discuss multimodal aspect of data in the second lecture today. Then the challenges that data comes with, a lot of noise, and sometimes data are incomplete. Quite often, many devices generate data keeping time and location as a reference, which means time and location dependent data are also a state of data that sometimes could be confused. Then dynamic, that means data is always changing and its quality is also changing because of the ecosystem and environment impacts. Most of the time, when you go for crowdsourcing of data, just like we discussed yesterday from traffic data, we think everybody is honest and sending the data, but it's possible that many data out of the crowdsourcing could be unreliable. But there is no way you can control that. Then many data, they need real-time treatment. So we have to do real-time analysis, which is quite a time not possible to make it process real-time at the edge because of device computing power. Almost all the time, we are concerned about privacy and security of the data that deal with. And this is the biggest, one of the biggest actually pain, for the data that we want to analyze. Now, data can be biased. So we need to know our data, that what is good, how much is mixed. All those details is definitely necessary before you are going to get the data analyzed and get the good result out of that. In spite of those challenges, we also have big opportunities. We call that big data opportunities. Broadly, you can say, with more data, more hidden gems are there. More the data, more the information, assuming that you have got good quality data. Now, with the more data, you can certainly going to have better informed decisions. Whether you are trying to make a prediction or strategize your goal, or you follow some recommendation system, then your decision will be better. For example, when you look at a scenario that, hey, I want to watch this movie from Netflix, then what you do, you go and check how many people have given it high rate. More people, high rate means that more data available, people are agreeing that, okay, this is a good movie. If only one person has given rating 5 out of 5, you will be hesitant, well, am I doing okay? Can I trust it? So that feeling also comes. So that speaks about more data, a better decision, or more trustworthy scenario that you are going to involve with. Then you can discover hidden insights with more data. And we have been discussing this issue last 2 days, that more the data is better, and these are the reasons actually. And if it's be it forensic or you want to check a pattern, depending on a pattern, out of 5 data versus 5,000 data makes different sense. And it can also give a trend, a good trend, a trustworthy trend. Then while you are trying to do automatic business process or make a robotic process implemented or language translation being done, so with the additional background, more information, more data, it will be always better quality solutions or answers to you. Now, which is the biggest opportunity for big data in your organization, be it in academic or enterprise? Some study was done a couple of years back, okay? Then 85% of Fortune 500 organizations will be unable to exploit big data for competitive advantage. But this story is no more the same, true today. It could be much less, could be 45 or so. Okay. Again, business analytics need will drive 7% of investment in expansion and modernization of information infrastructure. What it means that more and more people are driving to use data, apply analytics, and derive their answer or their planning. And this is now possibly gone to 80–85%. So this was the pie chart about the percentage of decision-making data, insight discovery data, and process automation data out of 100. As you know that data you collect, they could be structured, semi-structured, and unstructured, and their name, their title tells so what is the structured data, that it is following some database principle. All the information are safely stored without much error in database. They have a definite format with the limitation that not necessarily all data collected will be structured. The second point is, what is semi-structured data? Data may have certain structure, but it's possible that all the information may not be collected at the same structure level or same level. And at times, you may find some missing attributes, and a particular type could be missing more commonly than others. Whereas unstructured data is a very limited indication of data types, and they are least useful, but they could be used by improving certain parameters, certain attributes in them. But quite often, many scenarios we have seen, you start with kind of unstructured data. And there are ways to handle those data too, and the best example is actually your simple text document. And if you try to get some text spotting, then the data you get could be unstructured too. Things, data, and lot of it. We have been talking so many numbers, percentage, accuracy. That's okay, but what people want? The answer, not numbers. Okay? People want what I do with these numbers, zettabytes. How much is going to be good for me? So which means how do you get the answers? Who give the answers? Answers can come only by analyzing the data properly. Okay? If you consider a data life cycle, you will find there are 3 stages you can describe the data life. Stage 1, you basically call it metadata. Okay? When data is collected, they collected keeping a context in mind. They have some ID, some references in terms of location or time, that is when data is collected. It has a tag or not. Okay? And sometimes you can call this as a data by validating its format, its range, and a good source or bad source. And you can verify the data for its quality in terms of accuracy, consistency, or integrity. This stage 2, where once you get good data set, you go for data analytics. Data analytics involves computation. You have sometimes you store it, quite often unless real time, but typically you store the data, index it, aggregate it, ensure the structure, then apply analytics. And whenever you do for data analytics, usually you make some reference as benchmarks. You profile it against some benchmarks so that you can come up with some meaningful decision, not the numbers. Numbers can only justify the level of the quality of the answer, but informed decision is something big prediction or give a direction in proper way. Those are actually the descriptive solutions. Now, most of the time during data analytics or data analysis, you always adhere to some compliances like quality control, governance, and competence of people who have did the analysis. So data analytics is a vast topic. Data analytics is a technique using thousands and thousands of algorithms, both data-driven type or machine learning type, but they all have their own merits and demerits that we'll be discussing in future slides. So after analysis, you got data, you analyze data, make a decision, then you have built a confidence on that. After that, data is ready for the use. So when you do data analysis, pretty much you go for analyze it and maybe building a kernel, then use that kernel. That kernel is being used further on new data, because by that time you have built the trust, you have a right kernel to access and engage the new data coming in. Okay? And once you have that data, new data analyzed, you can display that using suitable visualization in particular application or applications. Okay? The secondary use could be security, providing licenses or allowing it to be used, using some licenses, and so on. Why we go for data analytics, but to IoT? Why IoT data analytics? Most of the answers possible you know by now, but we can quickly give a glance on those 5 answers. You like to establish a variety of a smart environment, be it a home or hospital. Then you have to analyze the data for some decisions. You want to make the lights on or lights off, make the sprinkler on and off, you watch the weather. So a smart decision is considering the environment, considering the temperature, humidity, and the wetness of the ground, a sprinkler system could be on for the house. Now, second is to uncover timely and actionable insights for machines as well as men. So, on time, decision on time to take certain actions. There are many possible scenarios. You have to do this or don't do this. Your utility has to be turning low or to be on. There are so many things possible in terms of actions, and those actions could be depending on the solution or the answer from the data analytics algorithm. Then third is to assist with precise prediction and prescription. You want to take some prediction that, okay, in next 3 days, will there be rain? Should I switch on the sprinkler or not? You can do prediction, weather predictions. Okay. Then prescription, so events are happening, and based on certain events in your mind, what you should do or what you should not do. To guarantee preventive maintenance of infrastructure, be it a power plant or automobile. In case of automobile, it might check various sensors. There are hundreds of sensors are equipped in automobile. It can tell you, okay, the air quality is bad, change the cabin filter, or oil quality is not thick and dark, you should change the oil. And there are many, many small deadbeats maintenance is possible by checking the sensor data and applying simple data analytics and take a decision on that. Then to ensure optimized utilization of distributed assets through monitoring is further, say you want to monitor fire in a forest. You want to monitor that, you see, you consider that the wind is conditioning, if there is fire or not, if the rain will be around, if there is water around or not. The many parameters are used and utilized optimally to take decision. And that process, you can also do measurement, then you management. If you remember the example we are talking about, say, associated vehicles for talking to using this node discovery example. So essentially, in that case, same issue is involved. So when we discuss our node discovery, we told, well, if something happens, emergency happens at a particular point, is looking for the solutions. If it's a fire, then fire truck, or some other thing that, like maybe you can go for a vehicle from the hospital. So you're always desperate in finding some nearby. So that will not happen until the situation is analyzed. Then next step is discovery. So we could not talk about analysis, but it's kind of there. So what are the features of IoT data analytics platform? Scalability is obvious because when you talk about big data, we talk about big ecosystem. And the query processing has to be very fast. Sometimes timely decision is important. Then flexibility and portability. Portability means you have algorithm, you have a technique, analysis technique that must run at the edge or at the fog node, wherever it may be, or at some scenario it could be in the cloud. So that should be portable from one level to another level. And fast data integration is necessary for analytic platforms. And quite often, you and an answer, the integration has to be end-to-end, so that all kind of data will be processed and analytics will be applied there. Machine and deep learning capabilities. okay, which means the platform should be capable of time-driven or statistical approach to analyze them. Then those two protocols at application level we talked about for HTTP or CoAP, sorry, HTTP and MQ CoAP. Okay, they should have actually these commands available for RESTful interface. Sometimes data analytics could be in memory or in database. So depending on that, you will be thinking about implementation on the platform. Now, if you are using machine learning, then when you want to use it? When you find human expertise does not exist. Human can't explain their expertise, such as speech recognition. I may be a great expert in somewhere, but if I go and try to interact in different language, it's kind of a challenge for me. So model must be customized, that is personalized. Medicine is an example. Every patient is different. They have different symptoms. It's dynamically changing. So a customized analytics only can help, and that happens, that is useful, or that can be realized using machine learning techniques. Models are based on huge amount of data. Genomic examples, okay? Genomic is typically you go for bioinformatics studies. Pharmacies, they do that. Now, applications are abundant in finance, computational biology, robotics, space exploration, and so on. So there are several types of machine learning. We discussed this yesterday also: supervised, unsupervised, semi-supervised, reinforcement learning. The reinforcement we did not discuss, I think yesterday. It's about the reward-based actions. Okay. So what are the models and how they look like? Okay. The analytic model could be one of those 4 possible types, as you see here, and your x-axis is arranged in a level of difficulties, and y-axis in terms of their importance or value. The lowest one here is called descriptive analytics. So descriptive analytics is about to tell what happened. Okay, what happened? If something happens, then descriptive analytics can give answer what happened. Because if you keep watching the data coming, and just going, coming, and going, being stored, you cannot make out anything until you apply descriptive analytics and say, hey, oh, something's wrong. The automobile has been getting more heat into it, okay? Our house is cold, so that something's wrong in its back. Then that's not the only answer. It tells what happened. Next is, why did it happen? That's called diagnostic analytics. If HVAC is not working, okay, house is not warming in winter, then the diagnostic analysis says, well, your HVAC is not functioning properly. Okay. Now, the HVAC can have errors in many ways. Either its gas light has been, they call this pilot light, it has been kind of gone out, or maybe the freon has been kind of, you don't need freon that day. In summer it could be freon issues. Then third thing is actually predictive analytics. It's very popular, and where you can use basically machine learnings. What will happen? You can predict. You can predict the weather, you can predict the stock exchange, you can predict the health, you can predict the, what do you call, your own result, even you can predict the questions that will come in the exam. Okay? So those are the few things you can predict. There are a lot of things actually you can do. That's the sky the limit. Then prescriptive analytics is very difficult level, maximum difficult level, but the highest value. That is, how can we make it happen? You are expecting something, you want something, but you have no clue except the data. So the prescriptive type analytics can tell this is how you can get it there. Now, each one quick descriptive analytics you see here that you have data they are available, and the BI, BI, business intelligence people, they have been using it for last decade or so. Okay, and essentially the descriptive analytics, as we mentioned last slide, says what has happened, what has occurred. Okay, and BI people, what they do, when they get data, they put that into various visualization graph like this. Some meter, some pie, some graph, some kind of regular graphs. Then you will find that when data changes, behave differently, this visualization also changes. The meter instead of here, it could be here, or it could be here. Okay, that changes. So that quickly said what happened. Okay. The predictive analytics is what will occur. So you will have some kind of visualization, some data, then you can always say the spot is changing, is flicking, or is moving particular direction, or data changes. More the data, your prediction could be higher. So there are algorithms for predictive analytics. If I am sure you must have heard about regression analysis, typically used for prediction. Machine learning, neural networks, they are also being used towards regression answers. So what will occur? Prescriptive, the top one, is more difficult level highest in the diagram over there, and we basically call that as advanced analytics, and it is used for critical resource allocations, because critical resource allocation is a NP-complete problem. Okay, to get optimal result, how much resource has to be given, be it memory management, be it network bandwidth management, or scheduling particularly. They are all critical resource allocation problems, and all the time they involve optimization. And that scenario is well known as NP hard. Okay, so luckily using neural net and deep learning techniques, you will be able to, looking at the pattern of data, you can come up with abstract the behavior, you can tell accurately what should occur. Okay. Yeah, this is detailed description of the what should occur. Basically, prescriptive analytics can benefit areas like healthcare strategy planning using analytics to leverage operational and usage data combined with data of external factors. So I would say that instead of forgetting any particular case, unless we are involved to do some particular domain, for all purpose, we can say we have resources available, we have an objective to do certain tasks, but the task to be accomplished in a way that if resources are distributed properly and do the action, that always is a pain, and we are able to handle that using your data sets that is available over larger data set available that has been watched or observed, maybe months, sometimes years of data depending on the domain and particular problem at hand. Okay. So applying your deep learning techniques, you can handle that. Data mining is pretty age-old techniques that we have been learning from in your computer science classes. They also, those data mining also being used as a form of analytics. And data mining has been improved over last decade towards more prediction activities. And you can always find the hidden pattern in a set of data that's stored there. So you can discover useful and unexpected patterns in the data. Okay? And non-trivial extraction is implicit, previously known and potential useful information from data are very helpful in data mining as a resource. Exploration and analysis, that is actually we typically go for a automatic or semi-automatic approach to explore the data and doing analysis. Of large quantity of data, you can get a better quality answer. We call that meaningful patterns. So these are typical techniques, operation, or we call it operation, we call it techniques, or analytics. They are always available and very popular. And classification, look at, if you want to prediction, then you have to classify, okay? And you can do regression analysis. You can do deviation detection, taking care of outlier, of course. Then use collaborative filters. It's very popular and very handy also. So these three, collaborative filter, and deviation detection, regression technique, and predict and classification. These four analytic techniques are used for prediction. We call predictive analysis or analytics. Then the other three, they are descriptive. Clustering is also descriptive. Association, rule discovery, sequential pattern discovery, they are descriptive. So we have in general data and types of analytic approaches. Now after that, I'd like to take your attention towards the IoTs. The IoTs at the edge. How do you apply analytics for IoT at the edge? We know that, we understand that IoT have constrained devices. Okay, there are a lot of constraints at the edge in terms of power, in terms of computing power, and real energy. So how do we handle that? We'll be talking about one particular potential solution in the next few slides, at least, that's being acceptable or accepted in the community. Okay, that's called approximate analytics. Approximate analytics. They call also approx IoT. Okay, approx means approximation. What is approximation? Nearby. So we don't have to do the details, but you take just like quantization also, something like that. Or sometimes you take samples, not continuous samples, sampling. Sampling, if you take sampling data, is maybe 1/10 or 1/100 of data. That's approximate solutions. And many scenarios you will find approximate solution is also equal good, but not necessarily everywhere you are going for approximate solution. If you are going for suppose doctor going for surgery, you cannot do approximation there. But you want to spot a vehicle location, you can do approximation. Things not go wrong, you go 10 meters this side, that side. Okay, but 1 millimeter this side, that side during surgery is a disaster situation. Okay? So you have to take it depending on scenario. So we'll take example of for IoT, not used for surgery, but we're talking about a scenario that where streaming data is being handled. When processing streaming data from different sources, as you see here, there are 4 different sources. Twitter is giving some IoT device connected to Wi-Fi, is giving some stream data, and maybe some stock exchange monitoring system, continuous providing data. So all these data streams are coming, and it goes to a stream aggregator, collector. Then after that, you build the packets, and basically after aggregation, you have to put to analytic systems, real engine. Okay, now this is black box. So we'll talk about that, what to do here. Then after the analytics block, it gives out useful information. So you get useful information, out of STEM analytics, and we'll talk example of approximate IoT soon. So approximate computing is something we're talking that there are many applications where approximate output will be good enough. Now, the proportion of a data is useful for this application. That means you don't have to consider all data, but only part of the data. This is a talking example, a live taxi heat map. Okay, taxi heat map means where you get a lot of requests. Okay, heat map is essentially those Uber or Ola, they have their cell phone ready and they keep receiving the requests. And very often at say 4 o'clock, school is closing, office is closing, they will get a lot of requests from there. So that point is called heat map. If you get answer 20 meters, 100 meters, this side, that side is not going to kill. So, but you can get it the answer much faster, where it is coming from. So what is the idea? To achieve low latency, that means getting result quickly, compute over a subset of data items, not entire data item, or subset of data items through sampling. So that way you can get the answer. You are using only handful of data set out of all, and though it appears to be approximate, but whatever answer is given there is just good enough. Okay? So this is essentially the flow is showing. You get approximate computing by sampling, take it and analyze it. And because you are using only a handful of sampling, you are able to process it very faster, analyze it quickly, and you get answers at little error. There is error bound to be there, but it's kind of not disaster. So a typical state of the art approximate scenario, there's a paper in middleware 2017 is called stream data approximation, where you got multiple streams, n streams, stream aggregator, they combine to get single stream, then go for stream approx analytics, then get the answer. And a cloud is essentially the one that is implementing this stream approximation. So it has limitation that it wastes some bandwidth, it utilizes only cloud data center as resources, but is okay as long as your answers are working for you. Now in edge computing, we know that the data to be processed at the edge or edge node before it is being sent to cloud further. Okay? So source of data at the edge, all the devices including mobile phones and the small sensor to more complex sensors, and edge node is the one having gateway, it has local processing capability, then giving cloud. So this is we know already, this kind of things, okay? It provides more computing resources at the gate, saving bandwidth. So much. Now let's make a problem statement and solve it before we close it. Okay? What is the problem? To build a stream analytics system by utilizing the cloud and edge computing resources. So the last diagram was saying, okay, I'm using something in the edge and also using cloud for doing my analytics, stream analytics. So we are going to have stream analytics in this edge system or IoT system who has edge nodes there and also connected to cloud or edge cloud platform. How? By leveraging approximate computing. In other words, this example is going to use approximate computing in a edge computing system. Design goal, efficient utilization of computing resources, that is in edge as well as cloud. Adaptability, that is adaptive execution based on available resources. Again, the resources are cloud and edge, and can adapt sometime using edge more, sometime using cloud more by moving it. No code change required and resource management. So basically nothing hidden, everything is transparent while implementing it. So there are n streams over there. The user making query, you have edge nodes, okay? 3 nodes on the front called regional edge, and some in the middle level called continental node. Then you have cloud towards the right. We call them central node or just cloud. Okay? So this is the overview of approx IoT. So approx IoT have edge cloud system with the input streams that you are going to approximate and process it. Some processing here, rest processing there, or sometimes process everything here depending on the workload. If it's more, it's going to pass there. So bottom line is, because it's approximate and stream is a continuous stream is coming, we cannot really capture everything that's coming in each stream. We rather sample at certain intervals and we take that as an input data for analysis. And we are going to use edge and cloud. Is this clear, the background, assumptions? Okay. Naive algorithm. There are so many ways, 2-3 techniques we are going to put together here. Naive algorithm is a simple random sampling. We sample randomly. There is no proper method to do that, just sample it randomly. SRS means simple random sampling. So out of say 6 black boxes, not boxes actually, they are black blocks, they call it, packets maybe, because when you get streaming, they are coming in a certain packets. Okay, then you, instead of taking all the packets, you take only few from each stream. This second stream is coming is maybe slower with less data. So there are 4 packets are there. You are sampling only 2. If it's 1, then you take 1. Sometimes you don't forgot to get that also. Okay, but when you do that, you can unfair sampling because you overlooked it here. Then query, you go to query because query is the place request comes there. So requester does not see or analysis doesn't happen on the entire packets in the front, but rather sampled ones. So query is actually your how do you call it, analytics approach here. So accuracy will be low because of the something overlooked. So certain stream is missing. The second approach is called stratified sampling. What is the meaning of stratified? You layered ones. You make actually certain layered ones or create the big stream into small substreams and try to sample fairly. You must take all the channels, all the streams without skipping it. Okay, proportionately. The disadvantage is it requires knowledge of each substream size. You want to be fair, but if you do not know a stream, a very slow stream versus a fast stream, okay, then if you're trying to provide some fairness, you may be also doing unfairness. So we need to have a good understanding the kind of input coming, the stream frequency, bandwidth, all those things coming, then you can take samples. So effective. So fairness has to be effectively done or proportionately done. The third one is actually reservoir sampling, that is more appealing for this particular example. Reservoir sampling it gets input stream, and there is always a constraint given to that the size of the reservoir. If the reservoir is 4, essentially even if input is 6 or 7, you can get 4 stream at 4 blocks at a time. So you get 4, the 2 are still left. The streaming, something more will come, but the chances of fifth block coming in will be probability 4 by 5. Okay. The sixth item will be 4 by 6, because your reservoir size determines that. Okay. Now advantage is no pre-knowledge required of subsystem size, because you are using a reservoir size over there. So we will take a little bit more deep inside it, because this is better and more appealing to the community. Disadvantage is substreams are sampled unfairly, possible, because your reservoir size does not change for all the streams. That's one speaks. So always you choose something, some fairness, unfairness, some uncertainty, certainty. So in this case, we are trying to see, because what is difficult problem? Difficult problem is to estimate or kind of think about incoming stream size. So we can, that's difficult thing. As I say, you try to do what you can do. You want to change something, but something you cannot change, just to forget it. Okay, that's not in your control. So the stream that is coming, unless it's a known project, a problem, I know exactly this is the stream, but that's rarely you do. There are other ways to do it better. So in this case, streams are coming, it's hardly difficult, it's very difficult to find out the size, but we can have a reservoir size fixed. That is in our control. Now we combine that actually, the previous one with the weighted sampling things, then we combine stratified reservoir computing, then we get it done. Let's see how we are doing it. Let's say you're getting a stream with weight function, weight for each one having weight W equal to 1, initial weight 1. Then we apply reservoir size n equal to 4. Then output of a weighted hierarchical sampling will be, you're getting size is 4. So see that you're getting 4 here. Out of 6, we're getting 4. So then weight of each one will be 6 by 4. Same thing. Here you get 4 to 4, but weight is 1. So 4 by 4 is 1. So essentially, if what is incoming is less than your n, then that's always W equal to 1. So for that, this is 1, but it's less than 4, so W also equal to 1. So this approach essentially can parallelize the implement computing too, and you don't need actually any synchronization between substreams. They're all independent, and that's why we're doing parallelization. Now WHS on edge nodes, same thing continuing. Now what we're doing here, we essentially posed the problem. Now we're taking it to environment, computing environment with the edge node and cloud. Okay. Now at the regional edge, if you analyze that, and let's take your reservoir size equal to 2, so which means you can get maximum 2 at a time. So you will take basically these 2 comes there, then next 2 will coming that way. So when you take any time 2 to the reservoir, then you get actually weight actually 6 divided by 2 equal to 3. This 2 is this way, n equal to 2, and 6 is incoming once. So 6 by 2, 3, and next it will be 4 by 2 is also 2, and this W will be 1 because this is equal or less than your size n equal to 2. In continental node, you do the same thing, then what is happening here is a little bit different than this, is the second level. So it has to be multiplied essentially. So suppose you have 5, okay, then pi by 2, 2 is the n, so you get pi by 2. Now, the weight of this incoming is 4. So, that is 4 times 5 number of blocks divided by 2, that is weight becomes 10 here. So, the weight was less in the edge node, but weight is more expensive for the continental node. Same thing is true here when you go for this double equal to 1. This is 4, this is 1, mind it. Now, equal to 2, number is 3 here, so basically 3 by 2, and this double equal to 1 multiplied by 1, okay, then whole thing is 3 by 2, the weight is, and double equal to 3, and since this is 1 is less than 2, that double remains as 3. So that essentially gives the weighted hierarchical, because you are doing nodes at the edge as well as the next continental node, 2 levels. You got 3 levels according to change, continuous like that. And we call that carrier weight because this weight is coming from the previous edge nodes. This is the current weight, that's why multiplying. This double 4 is the carrier weight coming from before, and this is the current weight because of just considering this scenario. So more the level, you will be keep multiplying it further. So again, it is easy to parallelize, require no synchronization between computing nodes. Now the cloud weights are still carried out, okay, then applied same rule, you get different weights now, new ones, and this in this case you are taking W equal to weight n equal to 1. So quorum is the sum or kind of final stage where you apply the analytics eventually. So that will be, you take what you are getting here with a number of blocks, then 4 into this and 2 into this, essentially. Weight, basically final weight times, then you can get the error bound. So what essentially telling that your approximate output will be depending on how to implement it. So given the example of 2 stages, the edge and 1 to the cloud, then the with a n equal to size, reservoir size equal to 1, 2, and 4, we saw different weightage, and with the carrier weightage and sum of products kind of thing here. So people implemented this actually using Kafka tools, multiple streams. They're doing the same thing. Basically, Kafka use the mathematics or the model that we talked last couple of slides is being used by this tool. Okay. See that the tools providing this and is going to edge nodes, then sample data stream coming, then essentially going to cloud data center. This is the platform that is being implementing the techniques that we just discussed. So they did some experimental setup. We'll wrap up quickly actually at this time. So experimental setup, the evaluation is based on the accuracy versus sample size, which means how much, what the size of sample will take, and the accuracy is reflected. There are 2 results we are looking at, accuracy and throughput, both versus sample size. Test bed use 25 nodes, 15 nodes for approx CIOT deployment, 10 nodes for Kafka cluster. They compare both the scenarios, tools as mathematics, numerical techniques, and using simulation tools. Data set, synthetic poisonous Gaussian distribution, real Basel pulse pollution, and some for New York taxi ride, a particular practical example. Now SRS and approx IoT results looks like this. So approx IoT is essentially staying at 0 minimum. Okay, accuracy loss means you're losing hardly anything. So it's lower is better. And SRS is actually accuracy is worse, but slowly falling down as you try to get the more fraction sampling, 60% to 75%, 80% maybe. So average is 0.035%. Okay, it's super degree better. Throughput, comparing with the NAV, SRS, approx IoT, in this case, throughput, so higher is better. As you save, the NAV is at this level, okay? So that means it is not giving any good throughput. Whereas your SRS giving good throughput, as the sample size is kind of a fraction is increasing, then things are, throughput is lower. Now, approx IoT and SRS almost agreeing to each other. So approx IoT has a low overhead compared to native execution. Approx IoT has similar throughput to SRS. So approximate IoT analysis for edge computing is the one for many scenarios, not that it's going to help every scenario, but particular example, specific example of IoT is moving. What happened? Yeah. Then efficiency-wise, is efficient computing and utilizes the bandwidth well. Is it adaptable? Adaptive execution based on available resources. How about transparency? It requires no code changes. Same code will work. Okay, this is the detail of the GitHub paper that we discussed. So we just completed the data analytics overview with one example, particularly the approximate things, which is very much elegant for the IoT cases. There are tons of examples you can come across. So at least you get a big picture now. That's possible what we can do in 1 hour to understand the big picture of the data analytics, how data is changing, and how analysis helps you, what is machine learning. We compare machine learning, deep learning in the other studies too, so they are part of this whole thing now, ecosystem. Okay? So with at least one working example showing that how sampling can help in scenarios. I can take a few minutes to tell you this sampling issue. We were working on a paper 4 or 5 years back, and my students are working almost 2 months on that and always coming with the results. The paper, a long paper, is taking ever, sometime 24 hours, sometime 30 hours, and it's showing me that. So it was frustrating. Then, that they say, if you think something continuously, okay, your brain is so capable that helps you back. That gives you answer. Okay? So it is bothering, so I don't know what to do. Then I said, why not to do one thing? Instead of giving the iteration next iteration one after one after one, you change to jump 20, then 20. Let us see. Because the idea has become very simple that I see this curve is going on, but it's going damn slow. You can't even make a difference between 5 and 7 or 8. So okay, then say, let's do that, let's see what's happening. They make a skip distance the computation. Then it happened that we did not lose any accuracy of the result, but latency is improved 20 times low, so which means it's great solution. But then you do not know what exactly I just randomly said 20, then you have to prove mathematically it's 20 or 30 or 40. Then that took 1 month to prove that. Okay, then throughput increased. Okay, so we got, eventually the paper was published very well. It has several citations after that, and we are able to make the throughput more than 1,000 times better compared to the other results. And that, what is that? That's sampling only. Similar scenario. It doesn't machine learning problem actually. okay, applied into aerospace. Yeah, usually those are linear anyway, so that those answers, okay, it's not something. If you're thinking about, yeah, no, it's also possible. Okay, that's a good insight though. Now, if you look at the curve is nothing but combination of straight lines. It's linear in certain portion, right? If you know how linear it is going, limitation where, you put bound there. You are just sampling, variable sampling, okay, or no sampling in the places of critical movement, dynamical changing, okay. So it was easy for us to do linear, but if it's different than linear, then we can adapt it. Adaptability is also another requirement. Okay. Another question?
Is there any possibility of missing required data by selecting the packet?
Possible. Yeah, it's possible, yes.
How to overcome?
It's likely that missing one or two data is not going to change a lot. When you miss a lot of data, that will be real difficult. A small error, you are doing a new approximation. You're missing one or two here and there is not going to make a big difference. Okay? You can do experiment and see that, how much you can tolerate it. You can also can tolerate losing 10% data or 5% data, or this is critical for me. That's another studies. They have not done it. Okay. Okay, doctor. They already asked, yeah.
In the lab, we have executed one CNN, one publishing algorithms, and we pull data structured and unstructured. That should be.
Yeah. Yeah, in 1 week, they can have a good exposure, and more they get involved with, and they should be ready to do research.
Also, we are providing the email address of you and mine so that they can get in touch with us to solve any of those.
Sure.
So the experiment what we have done, 8 experiments we have done on ML, that should give you a clear knowledge.
you are attending a photo exhibition, then in a town, maybe you are traveling, like me coming here, then I am talking to my friend maybe back home, my school, and there are photos about wildlife, architecture, so many things. And my friend, while talking to him and showing things in my phone and saw a particular wildlife item there, and he asks, can you tell me what is that particular wildlife photograph you are showing me just now? But you have no clue on the animal in the picture. Okay? And you can't even describe the photo. Okay? Little embarrassing. Okay? You are showing something, you don't know what you are showing. Okay? What if I give you an algorithm, okay, that could take the image as it is, its input, and automatically generate an image description for you. Just like these days, you take a picture of a plant, from the leaves it can tell everything about the leaf. Okay? Better than that, if your iPad can tell you what happens in the picture. It's not only what is the animal, but what is going on behind the scene. More deep insight about that. Now, question, is this possible that I just take a picture on my iPad and iPad it can give a description about the animal, tells me what's going on in the background? Answer is yes. How would that be possible? Well, you will need few things. You at least need two bits of information sources, two information sources. An information processing model for each source, a learning model to learn combined information. What is saying this here is the architecture view will be information source 1 and 2. And for each one there is a feature extractor involved. Then both the features are integrated, passed to aggregator network. Okay? So this is the architecture that will help us to avoid the embarrassment that we just came up. Oh, we have the same issue like yesterday. Okay? Yeah, the slide is kind of changed in a weird way. Okay? Now, so what is multimodal? Now, it's about sensor modality. Okay? We have a touch sensor, you have a sound sensor, smell sensor, okay, and appearance, taste, attention, all those, they are kind of different modals. Modal means sensing organizations. Okay? They are all together, you can say, multiple modes, multimodal. It's kind of sensor modality. So the modalities can be defined like this thing. Modality is about something that is being experienced. Modality is about the way, it's rather the way something is experienced. When you touch, you experience somebody touching you. Okay? You hear something. Okay? Those kind of things. Okay? Now, modality refers to certain type of information and or the representation format in which information is stored. So the representation, we'll talk about that. Is a techniques actually. Okay? Machine learning representation. Okay? We'll talk about that more because towards the end we'll be using this term so much, you will think of what is representation? I didn't know that. Okay? So modality refers to a certain type of information or representation format in which information is stored. How about sensor modality? Sensor modality is one of the primary form of sensation, such as vision, touch, all those things, channel of communications. The medium is, there are two things, modality and medium. Modality is something the way you experience some sensory activities. Medium, the means you can store and communicate. You need a medium, modality to exist. Okay? Medium is the means whereby information being delivered, sometimes being stored, so that proper interpretation is possible. So two things in multimodal we call modality and medium. These two must exist for processing. So example of modalities. NLP, natural language processing, not NLP, natural language, spoken or written, visual, from images for static or videos for streaming. Then auditory, including voice, sound and music, haptics, or touch, smell, taste, physiological signals like electrocardiograms, ECG, skin conductance, they are physiological signals. There are other modalities around there like infrared images, depth images. So they are all modalities that you can experience those things. For each one there is a medium existing there too. Same issue, all the pictures kind of 90-degree rotated for some reason. Okay. It's possible that the adjustment of screen, that might have been kind of, they could not accommodate this with the image, so it turned itself. That's why it's always good to use my own laptop than someone's laptop. Anyway, it's late to think about that. Now, multimodal communication behavior, how they behave, let more insight into that. If you look at your audio verbal things, okay, you have words, syntax, lexicon, okay, that's part of speech under syntax. Then pragmatic means disclosure acts. It is vocal, is annotations, then voice quality, all those details, features are there actually. We call it feature or behavior. Things are different way. If it's visual, it could be just a gesture or body language, or eye contact, or facial experiences, with more details there. And this shows actually similar things. Can you please interrupt. How many will you doing like this? This one also. This is the elevator. No, this, both are, yeah, but that was not done properly. Take it this also. No, this, yeah, bring down. Yeah, they have to fit here. This is fitment issue. No, it's weird. It's become weird actually. It's very weird. Yeah, no, small is weird in the sense the ratio is changed. Ratio, they call it aspect ratio. Aspect ratio is not correct. This is better. Okay. Oh. So like that, you have to do everything now. Yeah, it was like that. Anyway, what's this? Okay, let us go. We'll see. Hope there are not many like this. Now, this is something. I think almost all pictures have been screwed up actually. So next time you have a GIAN course, tell them not to use any secondary. This is really every class now have been seeing these things. Okay, it's not a difficult thing. We have our own setup, right? One monkey. I don't want my monkey to dance for somebody else. uh, Now, multimodal human-computer interactions, HCI. Now, you know, this is also not properly there. This has kind of gone somewhere else. Part of that is not there. It's under this title. Oh yeah, it looks like that. We cannot do that. So almost see, all the pictures are in there. I think we just stop recording. Yeah, this is not going to work. What can I do with this? These are answers. See? Oh God, that's not possible. Just call the doctor. No, this is, wait, what happens, they fiddle with the screen size. So the original picture, they're images, they have been adjusted for a particular background. Now if you take it and change, mass it, then this whole thing is blown off. The second one, next picture also same thing. It's not coming because it's gone somewhere. That's good. Huh? I don't know if it is.
Screen?
No screen class, no. Let's call Cyprocus. Call him.
Yes.
Yeah. I told him that just check a bit file before you start. You know, listen, it's taking things so easy.
Other laptop, any other laptop maybe is better.
I don't know. Oh, it's not working.
All images, all slides.
It's not okay. Everything is. So it's always you check it. You have time to check before you start the classes. They're all recorded. So next time you do
one should not say 10:05 or that should not say 10 because this will send a signal and it assumes that the vehicle is far behind it and then try to communicate and all, even though they are parallel to each other. So in such condition, in a distributed nature, when you have a distributed vehicles around in an area, and if the communication is not synchronized, then the vehicles will lose the track of the information and they will collide with each other. So the time has to be very specifically synchronized among all the devices. That is one condition. And second one is even in the robotic critical operations and all, they have to be synchronized properly. Otherwise, they will lose the commands and they might do whatever they want. So there are some networks which are time-sensitive networks. We want time has to be precisely be synchronized among the nodes. So this is a scenario where you see that we have the access points on the road or the base stations on the road, and the vehicles are communicating among themselves extensively for all the communication purposes, and they are trying to interact with each other so that they can move in a coordinated fashion. Otherwise, they will be losing the track of time and they might be moving faster and slower and they might hit each other on the road. Right? So if you try to see, we have a particular equation, D is equal to, you have D is equal to T into C naught, so you can easily find out. It is not that difficult to find out exactly what is the delay between two vehicles and so on, distance and delays you can easily find out. So the timing information also helps us to exactly locate where the vehicle is. Okay, it's not that the location will help timing. Timing will also help exactly where the vehicle is, or where the mobile phone is, or where the IoT device is. And if it is the timing is not synchronized, you will be losing something like around 10 to 100 meters distance. Exactly, you will not be able to precisely find out the location. So we have different methods of doing that. We'll come to it in the localization. We'll treat the timing information first, and then we go to that localization. So it's not only the location of the vehicle and all, even when we try to look into the MAC layer where there are a number of devices want to communicate among themselves, we want the media access to be also synchronized. Like the vehicle has to precisely come in the red slot and send the information or get the information. Yellow vehicle has to come exactly in the yellow slot and they have to communicate. The green has to come into the green slot and communicate. It is not that red can come in the yellow and communicate, or yellow can go into that. And even one bit jump over here spoils both the communications. So that is very critical over here. The timing is very critical, and they have to exactly come in the slot. They have to finish the communication, and next slot, the next vehicle will come, and so on. So this is one important thing, and it is in milliseconds. And assuming that it is 97.2K. If it is more than that, this will go into microseconds also. So we don't have these luxuries like we can do whatever we want at whatever time and all. We have to precisely use our timing. We have to finish off our communication and move out of it so that the next vehicle will come here, and so on. This is TDMA, so you have to move according to your slots given to you. So not only that, even the data fusion also we need it. Like when you're collecting the data from different sensors and we are trying to send it to the server, they have to be synchronized very precisely. So this node will wait for these two data to come in, and its wait time is 0.6, and if this sends to after 0.5, the data is lost. So when we are trying to mix the data also, the timing is critically important. When we are communicating, critically important. Finding the location, it is also important. So for example, we are trying to monitor the vehicle movement, the yellow vehicle movement on the road. And at 10:30, you have pointed out this, and 10:36, it is showing as 10:30.34, which means that in the scale, if you try to see, this is moving back of it. Right? In the time scale, if you try to see, this is supposed to be here, but it is here because there is a small delay gap over here between the timings of the two vehicles. it is assumed that this vehicle is moving backwards, not forward, right? So based on the timing, if we try to analyze, this vehicle is moving back, not front. So the timing plays so critical in case of distributed networks, and we have to give utmost care because the timing interval what we are trying to look at is microseconds and less than that. So now to get this information of the time, mostly we say that GPS is there and all, and or we have a popular computer network strategy where if you put on your laptop, automatically the timing information comes from server, it gets updated, right? Even if your mobile phone, if you try to see, it talks to the base station and get updated. You need not have to. That is what we call it as NTP, Network Time Protocol. They automatically move up and down, and then they try to precisely find out the timing using internet. And this is from the satellite, GPS satellite. And these two, if you try to see, they are power hungry. They are not that small energy devices and all. You have to get the information from the satellite, and it consumes a lot of energy, and your devices don't have that much energy to do that. So you can test it, like keep the GPS on your mobile, and you can see that the battery drains faster, right? So this is a very power hungry methodology, and does not suits for IoT. It's not only that, it does not penetrate to the walls and so on. We have to move to some other strategies rather than GPS. Okay? So if your IoT devices are in your cellular network, the GPS doesn't function. Like cellars and all. It's not cellular network, cellars and all. Right? So this is another big problem over there. And even nowadays, the indoor GPS we are not trying to use. We are using Wi-Fi timing extraction and all. Right? So these are some of the problems with the GPS arrangement, and we assume that it is not suitable for IoT devices which are placed externally outside and in an area where the GPS signal cannot reach that place. And even if it reaches also, we are not in a position to keep GPS on all IoT nodes because they drain the battery faster. And coming to the other side, this is heavily assumed that you have a lot of processing power. You can go up and down on the internet and get them. And you assume that always your server is on. Right? When you put your laptop on, you'll see the timing is showing some arbitrary value. But once it communicates with the server, you get back the timing. So this is dependent on your network, dependent on your CPU, and assumes that both up and down links are identical. And in that case, wireless networks will not give you up and down link, identical links. They are different. So to see that, what we do is we have a very small energy and a very small computing power and a very small memory. And because of this, we are unable to put heavy algorithms into the system. We want a lightweight mechanism to extract the timing information. And we need, if you try to see the IoT and all, we are not looking at IoT in the home environment, but we are looking at a application where you have more number of sensors and so on. Okay, we have to look into that type of connectivity. So basically, all the algorithms or the methodologies what we try to use for IoT, we want some master clock should be there. And with the help of master clock, all the nodes have to be synchronized. So here the master clock is not something that you are getting it from outside. On one of the nodes you keep GPS and see that all the other nodes get synchronized to that. That's the main stream of it. So here automatically when the master sends a signal, all the nodes will try to take their signal and adjust their clocks to the same value of the master. But it is not that easy, right? Because what happens when the master prop sends it, this node might be near to here and this node might be far. And if you try to synchronize everything to one scale, again there will be time scale difference, right? And the other one is, if this signal, even though I have drawn a straight line, it is not a straight line. I don't know the device, it is line of sight or non-line of sight. So the paths are not defined. So the timing extracting information will be random in nature. So in most of the cases, what we try to do is the clock is always a linear clock. We don't have non-linear clocks, so you can see the time progresses as the time goes on. We don't see the watches which are running backward or running fast and slow. All these things will not be. Most of the clocks, if you try to see in nature, they are linear in nature. They move according to the time. They don't run away from these times, right? So we express it as a straight line equation, mx plus c. And we know that k is referred to as skew and b is offset of the clock. And if you know exactly the skew and offset, you can know the timing of the information, right? But the skew and offset and all depends on lot of parameters, right? So when you see your watch, when you put a battery, new one, it runs properly. As the age goes on, it is decreasing the voltage. You'll see that sometimes it is slowing down, right? Over a day, it will not run 24 hours. It might run 23 hours, 30 seconds or something like that. It slowly decreases the time as the voltages decreases. So these parameters, if you try to see, it is not that easy to say that it is mx plus c. You have another parameter called as plus error. And that error, if we can model it perfectly, then you know exactly what is the time, right? The rest of the parameters are constant. Offset is a constant value. It is not that varies every time, right? The skew is constant as long as your environmental parameters like voltage and other environmental conditions are same, right? If you increase the temperature in the room, the clock might run fast or it might run slow. Or if you change the pressure values and all, it might have some effect. Because what happens is in the IoT device and the sensor networks, we want these items to be as cheap as possible. The price should be as low as possible. We don't, suppose I say the bulb is there, you buy it for 1,000, nobody buys it. So I have to bring down the price of the bulb to something like 100 rupees or 200 so that everybody can buy. So when I am trying to drop the price going on, I have to look for a cheaper items to integrate into the bulb, right? So if I pick up a cheaper quartz for the clock purpose, that will lose time because they don't have the accuracy is what you buy it from 1,000 rupees bulb you have. So now I have to compensate that so that the customer will be very happy, right? Even though if I take a lower cost item, I should see that the circuit behaves as if it is the costly item or the stabilized items you are trying to put it. So that is prime important. And for that, you have to do a lot of exercise. It is not simply you buy and integrate and get it, right? So, but ideally, the clock runs at a straight line equation, y is equal to mx plus c. And this is your skew and this is your offset. And estimating these two, in the absence of noise, it is perfectly easy. But in the presence of noise, it is not that easy. So this is what the clock is. So when you see 10 o'clock, it is 11, and 10 o'clock again you see it is. So if you take the real time 10 and 11, at the sensor node I, if you try to see if it is 10, it should be 11. And J, 10 and 11, if you draw it, you get a straight line, 45 degrees. Because both are running at the same speed. Both the clocks, as 1 and 2, they are running in the same speed. When this is 10, this is 10. When this is 11, this is 11. And it's supposed to be, the real time is 10, this is showing 10, this is showing 10. And the real time is 11, this is showing 11, this is 1. So both are running at the same speed, hence you get a straight line with 45 degrees. Right? You can plot it out also. 10 is here and 10 is here, 11 is here, 11 is here. Right? So now, if we try to see the equation, the relative offset, relative means the difference of clock between these two is 0. And the relative skew is 1. They are running at the same speed. So now, if you try to look at these watches now, at the real time 10, this is showing 10 and this is showing 02. And at 11, this is showing at 11 and this watch is showing at 11.2, which means that there is an offset of 2 from the both the clocks, if you try to see. There is a change in the timing. So there is an offset of 2, 0.02, sorry, it's not 0.2, it is 0.02. So the offset is 0.2 and the skew are same because both are running at the same speed. If this is 10, that is 10.02. If it is 11, it is 11.02. So the speeds are same. So the skew is 1, and you can see that there is a offset over here, 0.02, but the speed is same, so it is 45 degrees, right? So similarly, if you try to see here, the offset is delayed, like this watch is showing 10, this watch is showing still 9.58, which means that it is lagging behind by 2 minutes, 2 seconds, right? So they similarly here also, if you try to see, this is 11 and this is 10.7, the speed at which they are running is same, but only thing there is an offset of negative offset. It is not positive offset, it is negative. So you have minus, so you can see that the line has shifted here and still it is 45 degrees. So I think the terminology of skew and offset is clear. We are not changing those terminology. It will be continuing those terminology up to the end, right? So now, what is troubling us? So when a packet has been generated, this is a machine which generates the packet, right? Let us assume that there is an IoT machine which is trying to generate a packet. So it needs some time for pushing all the bits into the media. It is not that instantaneously there is a data rate at which you can transmit. So you have a pipe, you have a bucket of water. If you pour that, it will not go into it. Whatever is the capacity of the pipe only, you have to send it. So that's the meaning of the send time. You need some time to push all the water into the pipe, right? So that we call it as send time. The time required to push all the bits into the pipe, we call it as k bits by r. R is the data rate, so that will give you the send time. So now you have another time called as access time. So I am ready with the data, but the channel is not available to me. I have to wait for my time slot to transmit it. So for example, let me go back and, so red one has data, but it has to wait up to this point to transmit it. It cannot, just because it has data, it cannot push it over here. So that is what we call it as media access. You have a media, but you have to wait for your access time and then transmit it. So this is what the access time is. And then you have propagation time. The message has to move from here to here. The distance, if it is constant, the time period will be constant, right? And since if it is line of sight, it is constant. If it is non-line of sight, it depends on the objects which are there, helping them the reflected signal to reach. So for example, I have a food truck over there, and the signal is striking there and coming to me from the base station. And the food truck has moved away, it has to go somewhere else stuck and then come to me because it is a non-line of sight. So this is not a constant one in case if it is a wireless media. If it is a wired media, it is constant, right? Wire dimension will not change, it is fixed. So if you connect two devices, the wire length is same. Okay? So if it is wireless, we are not sure the signal, which path it is trying to take, and hence there is some randomness in it. Otherwise, we can assume that if it is a straight line or something line of sight, it is constant. And then we have a receive time. So the data, when it is coming, you have to wait for all the packets, all the bits to be received, and then only you can do something. If it is half bits of chem, you will not be able to do it. Until the last bit comes to you, you have to wait, and that is what receive time. The first bit and the last bit, whatever time you are taking to receive it. So now, if you try to look carefully, these are all random in nature. The first one, I have data, and the pipe is ready, so I can push it, but there is a limit on the bandwidth what is available. So right now I might have 1 MB bandwidth, next second I might have only half MB bandwidth, next time again I have 1.5 bandwidth, and so on. They are, it depends on the channel. Like for example, if you try to see your Gmail and all, downloading or uploading, the bit rate will be varying. It is not a constant one what you get it, right? At one instance you might get 1 MB, at the second instance it might be only 1 kilobit per second, and later on it might drop to 20 bytes, 40 bytes also. That depends on the load of the network at that instant of time. How much bandwidth you got it to transmit it. Access point, If it is time division, I know my slot when it comes. If it is not TDMA, if it is Aloha or CDMA or CSMA and all, I am not sure when it, because it is a carrier sense. Whenever the carrier is free, I can only transmit, right? So the access time is random. Propagation time, as I told you, the wireless networks, if it is short distance, you can take it as constant, but if it is a multi-hop network, then it will be difficult. Receive time also depends on the processor load at the receiver. It might be doing multiple operations, then the receiving might be slow. If it is free, it can receive everything. Like for example, I am at my desk and the mail has come. I can take it. If I am doing some exam paper correction or something, I'll ask, wait, let me finish up this and take it. Okay? So now if you try to look carefully, all these parameters are random in nature. They are not constant. And this randomness will try to create problems for me in estimating the time. Right? So I have to model this randomness such a way that I can find out my offset. Okay. So there are different algorithms which are available. It is not that there are only one or two methods and all. They are like you can see in the literature, you will have some hundreds and 200s type of synchronization algorithms, because most of the people, if you try to see, they used it for different applications. And all applications doesn't need the same accuracies. So they are dependent on different methodology. So they are popularly, if you try to see the initial stages and all, there are three good algorithms where you can call it as a benchmark algorithms, over which people are trying to compare their algorithms and say which is good, which is bad and all. So if you try to look like that, there is a reference broadcast synchronization algorithm, and which is very good algorithm. In fact, during that time it has a lot of popularity, but now people are not going into that because it consumes a lot of energy for synchronizing the network. And there is time protocol synchronization and FTSP, and we also have developed some algorithms in that direction. So if you carefully try to see this algorithm, RBS, what they primarily try to do is the source means the beacon, the node which has GPS and which can help the others to synchronize, right? So this is the master node. For example, I have shown you in the beginning, there is a master clock. So this is what is the source, and these are the receivers. So when we go back to the source tries to transmit the information. This is my clock, and all have to be synchronized to that. So now you have two types of synchronization over here. When the source says that this is the synchronization, it means that the source can get a global clock or it can be a local clock also. So some applications you need global clock because you are pushing this data into the internet. Some locally you are trying to monitor it, global clock is immaterial to you, local clock is sufficient for you because you are not pushing into internet and doing some applications and all. So like I have a monitoring station to monitor the attendance. So this is sufficiently fair enough for me to get the timing and put it. And even if it is 5 minutes or 4 minutes this way or that way, it will still survive because I am taking class attendance from 10 to 11. It need not be exactly at 10 or exactly at 10:05 or 10:10 or, okay. So in between 10 to 11 I can take a class. So I need not have to precisely go over there and come back. I can use a local clock over here. So this is what we mean it. So the source can have either a global clock or local clock, and the application will tell you what type of clock you need it. And then the master will try to send the information, my clock time is this. So all of you try to adjust it, right? So when it says it, the receivers, what they try to do is, the receivers share the information. I have received at this time. The another receiver says, I have received at this time. The another receiver will say, I have received at this time. So now you know the offset between you two. So the receiver to receiver offsets will be known to each other because I have received at 10.02 and he will say that I have received at 10.03. So the offset between we both is 0.101, right? So each one can calculate their offsets. So if I want to talk to him, I will adjust the clock such a way that I can talk to him real time. Okay, 0.01, I'll adjust the transmission time and say I'm transmitting a 03 to him. So I'll adjust 0.02 to him and say that this is my time, right? So now we are trying to locally do that. And hence, what they claim is, if you try to go back to over here, since you are sending all the people at the same time, this is common for all. And access time is also common for all. You have accessed the network and transmitted it. So these two has no meaning for me, and hence mine is more accurate. That's the claim they try to do. I hope it is clear. Because he is using the master clock to inform everyone, right? So the send time is common for all the people. The access time is common for all the people. So these two have no effect. The only time is these two, and that's what the algorithm is. And they inform this one is that, and they cancel out. The common two values, they'll get cancelled, but the rest two will be there. And hence they say that my algorithm is more accurate than others, because two of the parameters they have reduced it out of 4. I hope it is good over there, right? So coming to the next one, TPSN. And this is almost like your NTP protocol, right? The master clock, I got it. I'll send back the information. So the NTP mostly work on that concept only. There is a master server thing. You request it, they'll send the information, you request it and adjust it to your clock and do it. So now, if you try to look into that model, if the uplink and downlink are identical, this gives you a good result. And if they are not identical, then the problem starts, right? If the uplink and downlink are same, then you can divide by 2, because they use divide by 2, average of it, and then try to approximate it. And if they are identical, then you have the best estimate. If they are not identical, the estimate is wrong, right? So every node will have to do up and down. And hence you see that the broadcasting energy is more in the case of TPSN. And here also it is more because you have to talk to every node in the network. Suppose there are 1,000, all the 1,000 you have to broadcast. Again, the other one will again transfer to 1,000 nodes, and so on. And coming to FTSP, it is sender-receiver synchronization. It is almost similar to our type of communication. You can see the number of lines have been reduced, which means that it saves a lot of energy in synchronizing among themselves. You need not have to exchange 4 lines over here, 3 lines over here. Here it's only 2 lines. But the problem is we assume that the packet reaches the destination. If the packet doesn't reach here, we are not sure whether it has gone or not, right? So the only assumption is we are trying to send the packet, so you have to do it. So the change what we have made in our algorithm is we define that if you don't receive a packet within a bounded time, the packet is lost. You don't need to worry about it, right? So we fixed up the bounds on the time, and we are trying to minimize the error within the bounds. And slowly you reduce the bounds to a point where you can say that this is the point at which your time is being synchronized. So since we are using unidirectional, the energy is minimum because bidirectional consumes more energy. Up and down you have to do. You are doing only half of it, so you get a unidirectional one. And we have a very good paper in that ECTI transactions of electrical engineering and electronics and communication. So we gave you the complete mathematical treatment over there, how to analyze it, minimize it, and get back the values and all. And broadly, these are some of the algorithms which popularly people try to modify it and try to get a very good result on it. And you have to see that the error in estimating should be as small as possible within microseconds or nanoseconds. Because most of the devices, they prefer nanoseconds because in VLSI and all, the cross connects and all should be nanoseconds or less than that. So in that cases also the algorithms still try to help you out. So this is a small comparison between the FTSP and our algorithm. So you can see that these people try to use linear regression method to find out, estimate their clocks. And and the problem with this is they need larger memory because once you want to use linear regression, you need a data set for it. So you have to use the data set for, so you need a memory to store all the values and then find a linear regression for that. Okay? So the point estimation uses one single number, the best estimator for the error offset corresponding to the n data sets received. So mostly these people have done on single point estimate. Point estimate they try to do, and they find out the point, how much is offset, how much is skew, and so on. Right? And we have a different mechanism where we update the values. We don't store the values. Once we get a value, we update it to the next level, and we forget about the past. So the memory is not a demanding issue on IoTs. So whereas the previous one, there is a small slight catch over there. They need a larger memory. And the device, if you try to program it, you don't have space for the memory to store all those values. And hence we say that our thing is like updating the values. So if the old value is good, the new value will be discarded. If the new value is good, the old value will be discarded. Okay, so the updates the error interval after each message packet, and interval estimation uses a better estimate than a point estimate. Interval estimate is much better than a point estimate. That's what our claim is. And hence it has been accepted, and we got a very good feedback also on that. Any questions? So now we have used a 100 node network to find out how exactly the energy is consumed and all. And you can see that our algorithm is almost similar to FTSP. And whereas these two, RBS and TPS, are consuming more energy than the required energy. And this is in, you can see 10 to the power 5 nanojoules. And this is as the packets increases. So the, if you need 10 packets to synchronize, you can see that the energy is compared to the other two is very small. And the maximum number of hops what we got is 19 hops is the network. And you can also try to increase and decrease the number of simulations and all. Right? So this, oh, sorry. Okay. Okay, the localization part is missing over here. Okay, let me stop over here, and we'll continue later on in the afternoon. Okay, so. Yeah, good afternoon. I will try to continue from where we have left in the morning because I am left only with few slides before we actually move on to the demos. So the localization part, if we try to see, we should know exactly where the nodes are lying because we have many applications which tells us about the routing protocol. Suppose I want data from some part of the campus. I should know the locations of the sensor so that I can ask, okay, room number 302, report me the attendance status or something. So the localization helps us in finding the exact location of the target as well as the source. Source localization is there, target localization. So for example, if you want the target localization, you can think something like a ball which is moving on the track of a cricket field. You can exactly locate the ball, how it is moving, and all the directions you can notice it. Similarly, source localization also you can do it for finding out exactly where the sensors are. Okay, so localization can be viewed as source or target localization. It's not only one we are trying to do, two also you can do it. So here we have the basic requirement, something like we have to find out the location of the node by not going near to the node, because some places which you are not unable to go there, like suppose there is a volcano erupt and you want to monitor the situation continuously, you will not go near to the volcano. You drop the sensors around the volcano mountain and then try to monitor how the lava is coming up, what is the temperature, how the lava is moving, all these things you want to monitor it. So in such cases, we should know exactly the locations of the sensor so that we can track down the trajectory of the events what is going on. So it is not possible to find out manually. Manually, we will not go and find the locations. And the location information is required for some applications. It is not that all the things should need the location information, but some application demands, like for example, I want to monitor the line movement, that is target. So when it is moving it, I should be able to localize the target and see how the target is going on. Yeah, so that is what we call it as target localization. So when we are trying to do that, high precision is required, otherwise we'll be assuming that line is coming in this part, but it is moving 100 meters away. So the precision of localization is prime important in case of tracking the objects very accurately. For example, you might be seeing on the TV the ball is coming at the speed of 100 km per hour or 120 km per hour. So they are able to track it so accurately so that they know how the target is moving, at what speed it is moving, at what angle it is moving. Everything can be recorded. So this is important. And again, as I told you in the time synchronization, we are not able to put the GPS on top of it and track it because they need a lot of energy and these nodes don't have so much energy. So we have to look from the cost and energy consumption also, and we have to design our circuits based on that. So we have two types or classifications of algorithms. One is range-based, other is range-free. One is you try to find out the position. For example, I am standing here. I can easily find out my location, saying that if I know these four corners, I easily find out my location. I'll find out the distance from here, distance from there, and 4 points where they meet. That is my location. This is what we call it as range-based. I have to send some signal. I'll get back the response. Again, I'll send some signal. I'll get back the response. Again, I'll send signal. I'll get the response. So all these responses where they meet is my location. And there are some algorithms which don't need these ranges. They can find out where exactly it is. For example, if I say that where is Sai Prakash, you can clearly say that he is in the room number ECE conference hall because I am well within the defined area. Okay, so the accuracy will not be there in case of range-free, but in case of range-based, you have the more accurate result, right? But if you try to see, when you are going towards the accuracy, you have to spend more energy and cost and everything. If you increase the cost and hardware and everything, then you get more precise value. If you are not spending much of your work, then you can say that, okay, he is there in the conference room, right? So that is the difference between these two. One is cost-effective solution, one is like accuracy you have compromised for cost. Okay, so this only tells you like some applications like you just want to know where cybercache is, range-free is sufficient for you, right? Because in the department you can say that I am in this room, it is sufficient, right? But they want exactly what I am doing, how I am moving in the department and all, then I have to go for range-based. I will not be able to do it with range-free. Okay, so that's what is written. It is cost-effective. Much cost is not required for this, but here you have to put some cost on it to get back to the values. So now, what are the methods to send a signal and get back the information? So we have three popular methods. One is RSSI, one is time of arrival, time difference of arrival. And both are time of arrivals only there is a word called difference. So for example, I am trying to use some electromagnetic signal to transmit and get back the, like radar. So I send the signal, I'll get back the response, so I know the distance between myself and that corner point. So now let us refer the corner points as beacons. Beacons are nothing but the elements which know their location. Somehow they know the location, whether it is GPS or whatever it is. They are beacons which know their location, and from them I am trying to find out my location. So for example, if you try to see, most of the people, when you order something, they ask for a landmark, right? They don't bother for your address. You just say some landmarks. So you will say that, okay, I am opposite to the post office, or I am opposite to the LCT office, or I am opposite to NIT, or something like that landmark item you will say, and then they find out they use range-free algorithm. Because they need not have to spend much energy and all, come there and then call you and you will say, I am standing out and something, right? So that's what is range-free. You are not estimating, you are calculating your distances. You are saying that, okay, you come there, call me, I'll come out, right? Whereas here, we are not doing that. We are sending a signal and getting a response. Based on that, I am trying to calculate. So now the interesting part is, when we are doing that, we have one beacon, and I want to find out the range. So this is my target, or the sensor node, or IoT, and this is the beacon. So what I do is I'll send a signal, and I get back the response. I know that it is 5 kilometers away, or 2 kilometers away. And I will not be able to estimate my location, because it can lie on any of these 2 kilometer range. Right? I can be anywhere on the 2 kilometer range. Sorry, the beacon is here and sensor is here, so I assume that beacon is anywhere on the 2. Right? So with one beacon, we will not be able to estimate the distance. So now, if I move on to second beacon, so I will have another point which I will be trying to move around. So now I have an option that I might be either in this point or in this point. With two circles, if you try to draw the ring, there will be two intersections. So there is a possibility that I might be on this side or here. So the estimating your distance is not that easy with one beacon or two beacons, and a minimum of 3 beacons are required for doing that. So now I know that I will be lying on this area only. Right? So now I know that I am here, that this beacon I can hear it, this beacon I can hear it, this beacon I hear. So if I know the distances properly, then it is something like exactly you can cut at one point. If I know the distances accurately, you can see that the intersection of the 3 cycles will give me the location. So if it is 2, you have 2 points and you will not be able to estimate, right? So a minimum of 3 is required to find exactly where you are. But again, as I told you, your measurements should be accurate. And if it is not accurate, then you'll have a region over here, not a point, right? So whenever I transmit and get a signal, the measurements are estimations only. They are not exact, because I am not putting a tape and measuring. I am sending a signal and getting back. So they are, we call it as measurements, and those are not exact values. They are approximate values. So that gives me a small variation over here. And that itself will tell you how good your algorithm is. And if this is 1 meter, you can say I can predict with 1 meter accuracy. If it is 10 meters, you have to say that I am predicting your location by 10 meters accuracy. So always you might be seeing that the mobile lost and mobile somewhere they traced it and all. They say that 100 meters within the range, there is your mobile is seen over there. They will not tell exactly at, okay, this apartment, room number so and so, they will not tell you. In this locality only your mobile is there. Because they are using some 3 base stations, because they don't have so many base stations that they can send signals and all. So there will be 1 or 2 base stations or 3 base stations. So from that they can only estimate the location in that area, right? So now this transmitting and getting back the signals is what we looked at as received signal strength indicator. So if you try to see the signal received by your mobile, there will be 1 line, 2 lines, 3 lines, 4 lines, which tells you how far you are from the mobile station. So based on that signal strength, the algorithm tries to work. The second one is time of arrival. So I sent a signal, I got back the response, so the time difference or the time of getting the signal itself will tell you how much distance far it is, because you know the signal, electromagnetic signal travels at 2 into 10 to the power of 8. So you can calculate the distance. The time you know, the velocity you know, so the distance you can calculate, right? So now we have one more over here, angle of arrival, right? That is also a part of range based only. And mostly you need some extra hardware to find the angle, transmit and get back the angle and so on, right? And then what is time difference of arrival? See, time of arrival we know, we transmitted and got back the signal, we know time of arrival. Time difference of arrival is something very interesting, where because what happens is when you transmit a signal, the signal might hit the target or it might be coming from the neighborhood of the target. That is one reason. The second is, if you try to see, the velocity at which the signal is traveling is 2 into 10 to the power of 8 meters per second, which means that your measurement value will be microseconds. And measuring that microseconds will be very difficult, right? And that will lead to errors. So what we try to do is we send 2 different signals. One is electromagnetic, the second one is sound signal. So we know that sound is traveling at 330 meters per second, and the electromagnetic signal is traveling at 2 into 10 to the power of 8. So the difference of that, we use it for calculating them. And this gives you more accurate results than time of arrival, right? Because they both have started at the same time, but both will reach differently, and again getting back will be different. And please remember that this is not a bidirectional one. The beacons will send the signal, and I estimate the values, right? I am supposed to find my location and then tell others this is my location, okay? And once I get it, and once I get this error, whatever is the measurement values I got it, I have to compute this point, xy point, x naught, y naught point, once I get these signals from the beacons. And now how to estimate x naught, y naught. So we know that there is a Euclidean distance equation which tells you between x naught and x1, x naught and x2, x naught and x3. And just if you get your simultaneous equations and solve for E1, E2, solve this set of simultaneous equations, you get back your values x naught, y naught. right? When we use that, automatically you get back your values x naught, y naught. And now you have an error because you have not got the exact value. You will get some error. So you do it iteratively until you get your signal error difference is 0. So this E naught should go to 0. Until then, you go on rotating the iteratively. You try to modify, and then get back to EI0, which tells you exactly where you are. So what I'm doing is, as I get it, there is an error point. So I move this way and find the error. I'll move this way and find the error. Back and find the error. Which one is minimum? I'll try to use it. Right? That's what we are trying to do in that case. Now coming to the other set of algorithms, range-free localization. So it only gives you the centroid of a given beacon area. Right? If I can hear 3, I am there in center of, it is a triangle now. So in the triangle, I am there somewhere here. The other half, I am not there. So, and you go on decreasing your radius if you have more and more beacons. If the beacons are less, the error will be more. And drawing this centroid is also much easier. Now there is a formula for centroid. 5 faces if you have 5-face polygon, we call it as. So you can use the centroid of a polygon and find the location. If it is a triangle, centroid of a triangle, you can find out. Square, centroid of a square, you can find out, and so on. There is another method which we popularly use is graphical method. So what we try to do is, you try to take an area and you know it is there. Your sensor is there within the area. So now I move this one, displace it and see whether I am there in the area or not. Still, if I am in the area, I'll try to display it and try to find the area. If I am still there, I'll try to find it out. And now what I'm trying to do is, I'm reducing my error area. And I go on repeating it and find out whether I'm there or not. If I am not there in this direction, I have to move this direction or this direction, so that I know my location and go on. So this is what we call it bounded boxes type of algorithms, right? And generally we do this type of things for larger areas. When we have very large area, we want to converge very fast. We move the box very fast from one direction. And if you are missing it, we move on to the other direction and below, and we'll get to a location. And this is very easy in simulations, because in the simulations we write for x and y. So keep x constant, move y, and then keep y constant, then move x, and you get to the location, right? But physically, if you want to implement and see, it takes longer time, right? It's in a loop you are trying to do, and moving it one direction, it is simpler. And again, in a loop, other direction is also simpler. So mathematically, it is much simpler than actually going to the location and finding it out, because the equipment will not move like that in the real scenario. And the only thing is, if you want to do that, you need some drone or something which flies in one direction, one side, and next other direction, we can try it out. So this is about the general idea of how the localization is being done. And why we want to do this type of algorithms or location finding and all is important to us. Suppose people are saying that I have seen a tiger in that location. So now we can estimate the location where it is and try to monitor only that area. We need not have to monitor the complete area. So that is one precise thing. Like for example, as I told you in the first class, there is a fire accident and they have to report to the office. So suppose he has gone out of town and there is a fire. The office has to find out exactly where it is. It is not that somebody will call and then they will move and all. So the localization will help them to find exactly where the target is, right? Because the data which is coming on has some type of what you call it is, there is a deviation in the data, okay? So which means that data is not as it is what you are getting it. You are trying to find some type of, what is the name? We have done it? Anomaly detection method. So we find out anomalies in the given data set, and as and when we find the anomaly, we try to scan which area is generating that, and precisely we'll go to the location. That is one thing. So second thing is, when I want to move data on the network, I use geographical location routing algorithm to find out the location and go to that target, and only that target will be visualized. Like for example, there are 100 classrooms in the campus. I want exactly to find out the classroom 201 is active or not. I will not go through all the classrooms and see which room 201 and all. I only ask 201 report what is the activity over there. Right? So geographically, the sensor network or the IoT network should locate that one and go exactly to that and report what is happening in the classroom. And that is what precisely nowadays in most of the administrative block and all they try to do. The director need not have to go anywhere. He'll just ask room number 201 and he'll see what is going on over there. Right? And now since biometric has came, people are smart enough. So recently there was a query saying that the class has only 26, but the attendance is reporting 38. Right? I think it's a well-known fact in the campus. So he located that. He is watching one room, and he is showing that there are only 36 students, and the attendance is showing 48. Right? And now it has become another scenario, like teachers are supposed to monitor how many students are active in the class. So we are doing double duty, saying that, okay, so many students have come, and we take manual attendance, and we'll compare it. Whoever has done the fraud, we are trying to catch them. Right? So there are different ways of finding the location and how exactly we have to get into that and all. And there was one case also, like we have the biometric at the gate also. After the college officer who is going out and coming out, they have to be monitored. So they found one wax finger strip also over there. Recently it happened. Okay? So, and now it's not difficult to catch it. It is very simple because we know who has entered the data at that time. So we sent a note saying that you come and report. So later on the boy has agreed that he has done it, but it's not difficult. Like people should not assume that it is very difficult to catch and all. It is very simple to catch it because the record shows that you have recorded it. And the camera over there has shown that you have been passing through. Right? So the things are happening, but please remember that the localization helps us in saving a lot of energy on the network. You need not have to ask all the network to be active. You can directly go and wake up the IoT and then find out the instance. Okay? For searching the rooms, I need not have to put on all the 300 cameras on the campus and start searching for it. I can directly go to the room number, wake up that light or camera and all, and I can see who is doing it. So localization helps in energy and the cost effectiveness and the, what we say, the effectiveness of the network also improves. So with this, I am stopping on this localization and time synchronization. I have given you a brief idea of why we have to do synchronization, what are the methods available, why we have to do localization, what are the methods available. So we go to a range-based, you get more accurate. If you go for a range-free, less accuracy. The cost is less, implementation is less. Range-based is costly, implementation is hard, but you get more accurate. Right? And now people are trying to do a lot of research work on this, and they are trying to see with Wi-Fi can we localize the people in the campus or not. Right? In the department, I don't get GPS into this room, so I use these access points to find exactly where you are, because once you move around, your mobile is connected to the access point. I can know easily what are the signal strengths at 3 Wi-Fis, and I can locate your location. Right? So for that, if you want to have a knowledge of it, there is a app on the mobile phone which you can activate it, and you can find the RSSI of your signal from the Wi-Fi. And it also tells you how many Wi-Fis are in your range, what are their RSSI. So based on that, you can easily find it out. Okay? So with this, I'll stop over here, and we'll move on to the demo parts. If you have any questions, I can answer them before we move on. Okay, then, thank you. We'll start with yeah. So this is the demo part and the experiment part, or you can call it as. One is we have given you the experiment list also. One is agriculture IoT, and this is also part of agriculture IoT. We are trying to monitor the conditioning of FCI godowns using IoT, because you know that the FCI godowns right now has no monitoring process. They just dump it, and they are rats or rodents or insects and all. They try to move around, the water will flow around and all these things. So we want to make it semi-automated in the FCI godowns, and with that we are trying to look into how we have to look into the IoT for that godown purpose. Okay, next. So if you try to see the you can say the goal or the aim of the project is the rice godown monitoring system based on IoT sensors and device to track and regulate essential conditions for the rice storage system only. It is not for general purpose, only for rice storage, because you have seen that mostly the government will try to buy the paddy and then keep it up and then send to mill and get back, and all these things they will try to do. So we are trying to monitor 4 parameters directly: temperature, humidity, light, and airflow. And we are trying to use some conditions like a hardware part. But before going to hardware part, I'll show you a simulation path where you can use one simulator called as, there is a network simulator for IoT and sensor networks. You can use that Quantiki Collect. So there is a Quantiki software available. You can just simply take it and simulate your network, IoT network or sensor network. So we are using that Quantiki software, and there is a simulator called CUSA. So you can just simulate it and you design your own system and get the energy analysis, power requirement, everything over there. So here we are trying to use some IoT modes, like IoT modes means it's a hardware device like Skype, Arduino, like Arduino you have a Skype modes, which we are trying to use for sensing and find out the previous one. If you try to see, the previous one better. So if you try to see, these parameters are tied to Quantiki mode. Right? There is a hardware, Quantiki Skype hardware. To that we have attached these parameters, and we are trying to monitor it. Next. So this is, you have to define some of the modes as sender and some has to be a gateway to collect it. Right? We have the nodes as senders. They send the information, temperature, humidity, airflow and all. And we are trying to collect it and see how the network runs. So, next. So this is the FCI godown. We have placed around 30 modes around the FCI godown, because you know that the godowns are very large. It is not a small room. So from one end to other end, we have placed around 30 sensors. 37 nodes have been placed around it, and we have kept some nodes. We have defined it as gateways, which tries to collect the information, and the other nodes will try to participate. Whenever they detect something, only they try to participate. So it is event-driven type of network. It is not continuously monitoring it, because for continuous monitoring, we need a lot of energy for that. So it is event-driven. Whenever you see a rat or something moving, it detects, or something flying, it detects, or some moisture is there, it detects. So there is a Skype's web sense, so you can simulate temperature, humidity, light, and all, and you can use that SHT11 sensor only for that, and you can output it also. And there is some function inbuilt into it where you can visualize what is happening. Like earlier, I have shown you the sensor nodes placed and how the packets are being moved up and down and all. So you can see the packet movement also, how they are moving around and what they are transmitting and how many packets they have transmitted and all. Okay, next. So we have simulated that, and we are collecting that information again in Quantiki, and then we are trying to see the packet loss and energy consumptions and all in that network. So this is how the impact of the connections we are seeing, which node is transmitting to which one and so on. As we see graphically, the packet movement is going on. This is the central node to which everybody is trying to send it. If they don't have a direct connection, they go via some other node. Right? If the distance is far away, they take from other node and come to the collecting node and so on. So this is how the nodes are trying to communicate. You can see the node 2, node 4, node 6, and all, they are trying, node 22, and so on, they are trying to communicate. And you can see how the packets are flowing in from one direction to other direction, and they're being collected. So here you have a sensor map, and a node control also is there, where you can define the node for the parameters what you're trying to monitor, and the network graph, how the nodes have been laid down, how the nodes are communicating, you can see it. And you can have the power analysis, and the console is also there where you can monitor everything also. So this tells you the power consumption in the network. So the green one is the LPM, the blue one is CPU, and this is radio, and this is radio transmit. So the power consumption, if you try to see, the yellow one will tell you how much the power is used in the radio transmission. Right? This is the radio transmitted of the 30th node, and you have the green one is listening time, how much energy you are trying to spend in listening it, and how much you have been energy you spent in transmitting, and how much your CPU has used it, and your LPM is using it. So this is something like you can know how the nodes are energy being consumed. So you can see there are some nodes which are not doing anything also. Minimum energy, they are in a sleep mode, are spending minimum energy. So these nodes will be like something in the corner or somewhere in the middle, which the neighborhood is sending it, so they are not participating in it. But if you can see there are some nodes which are contributing more, which have to do multi-hop. Like the node, they are pushing it to somebody else and they have to do it. So they have double energy consumption and so on. So this is again the temperature measurements. You can see all are equally placed and they are spending equal. They are having the uniform temperature. The temperature in the FCA go downs are almost uniform in nature. They are not varying. Right? And why it is so? Because if you try to see the FCA go downs and all, they don't have windows and all. They'll be all tight packed and the distribution will be uniform. If they have small windows and all, then there'll be a flow of it and you can see the variations in the temperature. Yeah, that's about the quantity software and even so this is the file and this is what CUSA look like. You can see how it is being transmitted and all. You can simulate and show these visuals also, how actually the packets are being moved in the network and so on. Yeah. So the 37 is the node which is trying to collect it, and sometimes they are moving it. Once the energy is over, then they move to some other nodes and so on. So you can see the sensor map and the network graph. So at that time, this is the network. Next time, this is the network. It tries on the nodes which are participating only will try to form the network. Yeah. So వెనక్కి network graph. ఇంకా node control. ఇంకా ఇంత ముందు పేజ్కి వెళ్ళారా బ్యాక్ కాదు మీ స్లైడ్లో ఇంకా బ్యాక్ వెళ్ళండి ఇంకా ఇది వచ్చింది డయాగ్రామ్ అదే. So you can see here the way the nodes are trying to connect will tell you whether you are directly connected or you are going through somebody else also. That's what we are trying to see over the period of time, if simulatorically. So you can see that this is the collecting node, and mostly we have kept only star topology. We have not kept bus or something else. You can define the network structure also. It is one hop only. Mostly we are trying to see that it goes one hop. In case, worst case, when the node is here collecting and some node is here which cannot reach, then they go by a hop. Yeah, sensor skill. No, here we can see that they are mostly star connected. They are not going in multi-hop connections and all. Next. And the temperatures are also uniform throughout from 1 to 30. All the nodes have the uniform temperature around it. So this is how the network hops are moving, 1 hop, 2 hop, 3 hop, maximum it is going to 3 hop. Otherwise it is remaining at 1 hop only. Mostly they are in 1 hop. At times they go to 2 hop and sometimes they are going to 3 hop. That's the maximum thing which it is trying to take. And this is the received packets per node. First node have received 3 packets, the third node only 2, and so on. So last 5 minutes, if you try to see, those are the things, and this is the power consumption on the nodes. Each and every node, you can see how the power is being consumed. The average powers are coming up, yeah, and that is in milliwatt. So if you have a battery of some 1000 joules, you can know how long the node can survive. And this is the duty cycling, we call it as radio duty cycling. We can see that the red one is the node is listening and blue is sleeping. Blue is transmitting. So we have not kept any sleep mode over here. They either receive or transmit. So most of them they will be in receive mode, and the blue thing is they are transmitting. So you can see the transmitting is very less and receiving is more. And this is instant power consumption. Every instant you can see how much power has been consumed. And this tells you completely what is happening inside the network. This is one thing which we can do it before actually we put the hardware in the godowns and all. Right? We can analyze, like if we put this type of battery, how long it survives and what are the locations which is good and so on. So now you can play with the locations also and see that the energy consumption can be reduced. And if there are more number of sensors, you can reduce them also. You can switch off some of the sensors and see how the power is being consumed. So if you know the ideal places, then going there and installing will be much simpler. So this is one simulator. It is free of cost, and anybody can download the Quantity software and try to install it and see it. And they can define their own modes also. Here he has used the Skype nodes. So we can see the complete analysis of how many hops, lost packet, dropped packet, received packet. Complete analysis we can know. Like if you have a network, if you transmit it, whether the packet has been received or dropped or lost, you can easily find it out. And this is very good if your network have a user density more. If it is user density less, you will not have any dropped packets. Right? If the number of users are very less, there is no question of dropping the packet. If the number of users are more, then we can really see the drop of packets. Right? Okay, that's about the software and simulator, which if possible, I think you can use it as a lab simulator and you can use experiments on that so that the people knows how to see a MAC layer and how many packets are being dropped, how many are being transmitted, and what is the power consumption. These things they can easily understand. Okay, so we'll stop about the collection of data and how to simulate it and all. And we'll go to the agriculture AI. Oh, and in the చూపిస్తారు websense dot c. This is కిందకి వెళ్ళండి. Yeah. కిందకి వెళ్తారా? So this is what the programming part look like. What we have written the program for that application. So we are trying to find out temperature, humidity, light, pressure, and these three, and we are trying to put it in a file and try to find out the averages of that and then trying to put it on the graph. Right. So this is the raw humidity and how to find out the humidity offset, and depending on the SH311 sensor we have picked it up. So this is the code what they have written it for the request time and all these things. Yeah, in that you can program it. You can write the code and you can modify the code and all. Yeah, C language. Python also it takes. C basically they have written the quantity for C because it's a older version. It is more predominantly for the C. If you want, we can share the file also for you. Right? No, దాన్ని modify చేశారు కదా మీరు. See, there is a source code available and it has been modified for that. So, ఇంకొకసారి రన్ చేస్తారా? Yes. రన్ చేయండి కోడ్ simulator లో. సిమ్యులేటర్ వేరే పెట్టండి, సిమ్యులేటర్ పెట్టండి ఒకసారి. సిమ్యులేటర్ ఆన్ చేసే ఉంది కదండి, ఆఫ్ చేశారా? ఓకే, యా యా యూ కెన్, యా యూ వాంట్ టు స్టార్ట్? యా యా సారీ పెట్టు, యా నో విల్ టేక్ ఇట్ అప్ ఆఫ్టర్ దట్, యా.
So now we are back. So the last slide was talking about as a multimodal communication behavior, which essential talks that, okay, in visual, what are the behavior, the different kind of communication behavior you can find, starting from just gesture. Two people can just talk to each other using gesturing, and gesturing could be either head, eyes, arm, different kind of gesture. Then body language, also eye contact, head gaze, eyes gaze, just kind of looking somebody, staring at, those kind of things. Similarly, vocal also, you have a different way you can communicate, behave in under each categories. And it is verbal communication, this could be just using words or part of speech, okay, and discourse acts. Okay. Here you can say that the communities means people that is engaged in certain behavior, in certain mode, certain sensing activities, sensor activities, and as a speech community of all kind of communication. In vision, just it could be just a one-dimensional, or it could be video, it could be static, image, all those kind of, including all this behavior you saw on the last slide. Then multimedia, we have got both audio, video, and other things. We'll talk later. Now, the communities essentially says, okay, they explore all potential mediums, all potential sensing activities. The community is not just user, they could be also research community too. Okay. Here is an example that multimodal human-computer interaction, or HCI, how it is possible. Even you can set up an experiment accordingly. As you see, here is the person. Okay, here the person sitting here. Let's call him user. It can have various type of communication, which essentially will be combined here. Now, let's think about a speech. A speech synthesizer, it gets the fixed speech mapping. At the same time, it can switch between these two ends, and here you can get multiple mediums, multiple sensing activities, okay, such as a vowel network, consonant network, and your VIC decision networking. Everything combined can go here, or a contact switch can be available to fixed stop mapping. And that also is possible. And you can modulate that using a pedal control over there. Okay? So all you can see here that it shows how to design and evaluate a new computer system where human interacts through multiple modalities. It's just a framework, is a emulating framework. Both input to and output modalities could be combined or could be presented. Okay? Now, a neural network interface is also possible when you try to do some data processing over here. Now, we need some rules or models. these models are, there are many models, but more popular models in this area are hidden marker model. In the hidden marker model is typically you can predict something. You are following certain pattern, then you can predict based on the pattern. Okay? And there are two kind of hidden marker model is a factorial hidden marker model or coupled hidden marker model. Now, in this case, you go for multiple state variables to represent the hidden state. Okay? Now, for example, we want to, for traffic, and this is something actually we know already that this weather modeling, traffic modeling is being done in the same process. Now, more additional models are being used in this area for multimodal computation, which are ANN, backpropagation, or simple CNN. Okay? And under this, for this multimodal computation model 2, you have, hope some of you heard about dynamic Bayesian models being networks. Okay? Then there's a reference actually, if you don't know, it's a very powerful model being used in many disciplines. Then Kevin Murphy's thesis and MATLAB toolbox gives very details how to implement things. Okay? Then this is an example showing okay, how audiovisual speech segmentation is possible using artificial neural network. Not that we are solving it, but it's kind of giving a feel that you can use various models, ANN, CNN, segmentations, as well as dynamic Bayesian networks. Okay. Now, how deep learning can be used? Okay. Now, one thing I can make it clear to you that whether just machine learning or your DNN, they are typically representations. So, representation is a term that said that how you can take the problem, represent in certain way, okay, and any media, any modality can be modeled using that. Essentially, the modalities, multimodalities, they could be imposed in representations. And here, your DNN is a typical deep learning, is a representation for multimodal applications. Okay. Now, it is possible that because you are using an abstracted deep learning phenomenon here, now large-scale multimodal data set could be printed by that. And to compute that, knowing that deep learning has a lot of computing overhead, you engage GPUs for getting the abstraction of the data. Okay? And high-level visual features are possible just taking the result into a visual format. And multidimensional linguistic feature is also one of the attractive feature or a key enabler for the multimedia research. So what I told there, it's kind of a representation in general, but this slide is going to show you the real world problems by multimodal research. Now, if you look at people's face, different kind of face, disgusting. This face is a kind of anger. So various emotions, okay? Similarly, you can have a persuasion type of show and the personal traits, okay? Now, in a way, why I'm showing this to you? Why it's important? First of all, definitely it's real things. Now, suppose you want to do some emotional analysis. Okay? You want to see somebody is going to do shopping. Camera is given there. Customer is doing shopping. And when you buy something, suppose buying a cloth, you may like it, you may not like it. If you don't like it, sometimes body language, emotions, they express that. So it's possible that somebody can watch it, can know whether this person is going to buy it or not going to buy it. Okay? So this is just one example. There are many examples you can think about how emotion could be used. Similarly, a patient is in pain or is comfortable. From facial expression you can see that. Okay? There are many scenarios we can always think. Similarly, pursuing. You can even know whether when you talk to somebody, you can pursue from the expression, from the gesture, you can know, yes, I can pursue further to get my things done. Okay? It's used for business negotiations and dealings, contract dealings. And also, media descriptions. Given a picture, they say that picture is a description by 1,000 words, okay? Better than 1,000 words, okay? Now, from each, you can say this is a place, is a play home or kind of play schools, okay? Somebody is in accident or playing. So, given the picture, it is possible to get things described. That's where we started that, okay, if you have got at least two inputs, then you extract feature independently, then you combine them, then you can figure out the background about the event. Similarly, you may not have image caption, but you can create an image caption. If you are a novice news reporter, somebody gave you a picture like this, you can always come up with a very beautiful image captioning. Okay? Similarly, video captioning is possible. You play the video, then automatically captioning will be coming up. They are actually smart technique of using various tools that we have and abstracting it given the video or image. Okay? And sometimes also you can get a visual question answering the same way. Another example or problem is the event recognition. Okay? Something what is happening in each case. Somebody is doing yoga, or somebody is trying is cooking. Things are what is happening. Now that's possible using either recognizing the action and segmentation. The two sources you can use it to find it out. And multimedia information retrieval is another area. So given some images from past without details or details mixed off, you can recall that as content, then you can always find it out. So the real problem to tell you that, hey, here are the amount of work involved there. Now, there's a nice paper with this reference, okay? There are on multimodal machine learning, there's a survey paper. So with the details about representation, alignment, fusion, transition, and colon. I thought these are the challenges of machine learning, I guess. Okay. Challenge one, I think something is mixed up here. Yeah, something is missing here. It should be challenges, okay, challenges. So the challenge one is representation, okay? Now, we're talking multimodal representation, right? So the definition is learning how to represent multimodal data in a way that exploits the complementarity and redundancies. Let me read it again. Learning how to represent multimodal data in a way that exploits the complementarity and redundancies. Look at this plane. Okay, let's say we want to capture something, a surprise, or some word like, this is actually, what is this? Using visual, right? Then somebody says, wow. They both, two sources, they tell the same thing. Okay? And somebody says, I like it. Giving consent, good gesture, okay? And from the face also you can do the same thing. And you can hear the tone. A written text, a tone, joyful tone, and from the expression. You can confirm more than one, two, three sources that say the appeasement, pleased, okay? And here, scary, a tense voice and from face expression. So that two modality, they can be combined together to express a different emotion and different things, okay? So what to do actually is given here. I'm sorry for the blur diagram, so probably I have to take care of it later. Okay. Now modality 1, modality 2, okay. 1, 2 could be 1, 2, 3, 1, 2. Okay. They essentially are together to get a representation. Or a representation could be combination of 2, either way. Second challenge is alignment. These are multimodal challenges actually, and how to resolve to some extent. The alignment definition is identify the direct relationship between elements or sub-elements from 2 or more different modalities. Just like we saw there, previous one, this is one modality, this is another modality. There are 3 modalities here. Same thing here. How do we align them? Why need alignment, by the way? To find some commonness. If you align them, you can say, yes, they are of same category. They can conform or complement each other. That's complementarity, okay? Complement each other. So you have, say, modality 1, you have components or sub-elements. Modality 2, you also have many. You have n here, n here. Not necessarily T1 is aligned to T2. T1 is for T4, T2, T5. Some way you can find alignment. As long as you find a good number of alignment, then a representation will be good. Now, explicit alignments. The goal is to directly find a correspondence between elements of different modality. The picture shows here. Okay? I call that fancy alignment or whatever, right? Then implicit alignment uses internal latent alignment of modalities in order to better solve a different problem. So what is the difference between these two? One is direct, one is implicit. So it means you have to extract those things. After extraction, you can find alignment. The alignment could be already exposed, or you have to find it. Look at implicit alignments here, example. Now let's say, look at the word. A dog with tennis ball is swimming in murky water. Okay? Now, in this picture, you see the tennis ball. Okay? Tennis ball is here. And there's one dog. Now, if you look at these 2 words, tennis ball and dog is gone, then swimming in murky water. So swimming is happening, and swimming is associated with the murky water. So you are associating, aligning swimming with water. You cannot swim in the air. You cannot swim anything else. Okay? So that's basically alignment. And it's possible that we can have a ball, just ball picture there, and with dog holding that in the mouth. Okay? Now, you might see a picture, but you want to find out alignments. Okay? When you write something in a text, and you try to, a text is one representation or one modality, and picture is another modality. So that way you can find maybe part of them. As you see here, you are not able to see everything, but as something is able to match. The fusion means putting together, joining. So fusion definition is to join information, putting information together from 2 or more modalities, okay, to perform a prediction task. Now, again, you can have a early fusion or late fusion. Now, the model agnostic approach, okay, in spite of model, without model basically, okay, is in early fusion you get 2 modalities, 1 and 2, okay. You try to merge them, and a classifier is applied there, like clustering or things like that. You get them, okay. And late fusion, you apply the classifier at the input like this, then you merge, you basically go for fusion. Fusion means combine or join. You combine, before combining you classify here. Both modalities have been classified, then merged. Here, both are merged, then classified. Okay? And then you can compare which one will be better in which scenario. Then a model-based, this is model agnostic means without model, just common sense. But this one is actually using model as an intermediate approach. You can use deep neural network, you can kernel-based methods or graphical methods. Okay? So these are again representations. Then you can find out different views, some views here, some views there, with this, and say which one is more of, working better. Translation. Translation is a process of changing data from one modality to another. Just like language translation, for example. In representation could be in one language, not representation, the input could be in one language, one modality, say Chinese is one modality, Hindi is another modality. Okay? Now you have to translate them, and before translate sometime you have to find the relation. So how translation happens? They try to find a relationship, and they find a pattern of relationship. That's called a feature, or you can say underlying kernel. And more they see, they can find how language translation happens. They can find those key points inside hidden in the, when they have millions of translation, watch it, observe it, they try to find out those things in translation. And they build actually a rule that is essentially going to help. Now, sometime it could be model driven or just example based. Example based means in such small sections, okay, this is source, then this is target. That's how the translation happens. Another source goes to target. And these are the, what do you call it, repetitively observe when you break those two languages and try to find relationship, translation relationship. Okay? One is the source, blue color, and target. Source to target is a phenomenon that is observed or underlined or hidden in the translation between any two languages or image to language, could be anything possible. Okay? Now another one is called model driven. Okay? That's difference is what I told here, that you can pretty much go and find the rule using suppose your DNA or something like that, then that actually is model based. When you don't use model based, you try to get a small piece and said, I give an example, I notice all the time, if I'm starting with this, it relates to that. And this is a pattern, example repeatedly observe. That's why it's called example based. And this is model driven. Obviously, example based has a lot of limitation. For large scale remote languages, is it hard to get. But model driven is a more automatic process which can be feasible by any manner who want to implement it. So for this, you may have to do first training, then using the kernel of that, then go for the translation. The fifth challenge is co-learning. Co-learning refers to transfer knowledge between modalities, including their representations and predictive models. So two things, both representation and models. So you have modality 1, modality 2, you may have a way to compare them or set them, put them in framework, and get the prediction from each of them. Okay? Now, given the modality essentially is having hidden data. Okay? Now, from data, you always get knowledge. And you find actually knowledge there's some common knowledge you might be finding between them. Okay? It's about at what level you are trying to get that. And to get that level, typically you try to learn, you have to learn the existing modalities well and derive knowledge. And to get the knowledge, basically you go for a learning mechanism. The word co-learning here, because you are trying to learn from both the modalities. Okay? It's a same example saying that, okay, you can do learning using given data set from like parallel, at the same time try to find through co-learning between two blocks here, and here non-parallel. Some scenario may not allow to do parallel, then non-parallel means you can basically skew sets. Dot dot means not straight line, they're kind of connecting other ones. Then another one is hybrid. Somewhere it is direct, somewhere it is non-parallel. That combination is called hybrid. Now, keeping everything together, that's called taxonomy of multimedia research. You have a representation such as a graphical model, neural network, sequential, similarity, structure. Okay? These are your representations. Okay, remember this thing, okay? Because we will be using it in slide. Then translation, retrieval combinations, model-based or example-based. Then alignment, explicit, implicity. Fusion, early fusion, late fusion, and hybrid fusion. Or could be model-based. This is model agnostic, is with model-based. And we just discussed about co-learning. So it's everything putting in one slide. And this is an interesting table where you can watch, you have representation, the challenges, representation, translation, fusion, alignment, co-learning. And here you have some of the applications. Speech recognition and synthesis, event detection, emotion and affect, both recognition and synthesis, is action classification and multimedia event driven. Media description, 4 possible subcategories and application. Multimedia retrievals, either cross-modal or cross-modal hasting, retrieval and hasting. So if you see here, all of them have some representation, possible to do representation, all of them. See? But when it comes to translation, all of them are not, all applications are not suitable for translation. Speech recognition is one doing it. Emotion, yes. Some media and some multimedia retrievals. Similarly, fusion, not everything but some of them. Alignment, some of them. So one can actually justify these things by thinking a little bit and checking why translation is not here. Not here. Okay? Okay. We've done some basic discussion about representations particularly and challenges. Let's go to the real multimedia IoT elements. Then we jump into actually multimodal computing, the rest of the slides. Now, here what is this called? MIoT. MIoT means multimedia IoT. So, to process multimedia IoT, what do you need? Element means you need, what are the processing entities you need? So, what you need, the first one is identification. You have to, any data is coming, you have to identify it. An object is coming to identify it. Okay? Then, after that, you go for, what is this, physical object? I can't read that properly, that's kind of so blurred. Yeah, physical objects. Okay? Identification, physical object. Third one is communication. Fourth one is middleware. Fourth one is, yeah, essential. This is the key. This is the key we'll be focusing, because you know already these things. You know this. All these three things you know. You may be knowing something, but I will clarify this. But you know this thing, physical layer, you know this, communication, you know this thing. Middleware also, we know, but I can always talk about a little bit. Then this is the one that we are supposed to discuss in detail. Then application also know it. Take one of them each other. So what the first layer was identification layer. So identification layer means we are talking about multimedia IoT. So multimedia IoT is using some objects, some gadgets, be it a camera, a sensor, or be it another type of sensor. We call it sensor object interchangeable, I am calling them. So all those things you buy, they have a ID tag, all of them. What we call that? We call that EPC. Every electronic product has code. Okay? But what happens is these products, when you buy, they not necessarily change the EPC number. Suppose you have got 3 or 4 objects, they will have same EPC possibly. But if you have only one of each type, then that's fine. Your EPC will be unique. But also sometimes you get actually U-code, ubiquitous code, or U-code in general. Now, if you find there's a kind of confusion or repeating, all you can do is, since each of these electronic product, they are a part of your wireless sensor network, they basically equipped with that, then they could be either IP4 or IP6. Then, which means you can identify, you can provide a tag or ID using that IP number, okay? IP address, because IP address is always unique. So which means you have 3 choices: EPC or U-code or IP address. So that's how you will be identifying each object involved in the identification layer, bottom layer. So physical object layer could be either scalar objects or multimedia objects. Okay? So because the physical object layer with the multimedia IoT is responsible in collecting data from various objects within the network, then and transmit that to central repository for further processing. So we classify these objects either scalar object or multimedia object. So what is scalar object? Scalar objects are typically characterized by single modality. Okay, single modality could be just maybe vision or audio, those kind of, or text, just one. Whereas multimedia object may be single or maybe multiple modalities. Think about a video frame. Video frame is having is both having image as well as speech. But an image is just a single modality. It's a multimedia object, but single modality. But it is multi modalities. Then the characteristics, to characterize the objects with the different modalities is a characteristic of the MIoT, which is different from traditional IoT. So what is saying that to characterize, depending on scalar or not, we have multiple objects, but each object has a unique identification, and each one also belongs to certain modalities. So we pretty much tag them together. We characterize this ID, this modality, this ID, this modality. And that way it will be easier for doing management and the processing, data collections. In communication layer, within the MIoT, a same function as a traditional IoT that we discuss in sub-layers like link, network, and transport layer. Okay? Now, and these components essentially also support the MAC protocols, okay, and different topologies. And typically we use star topology, and star topology is used to connect the full function devices to reduced function devices. Okay? But mesh topology, in the case of mesh topology, they always connect the full function devices. Basically, in a device world, when trying to do connection, you will always find some are having full function like OS and other analytical computing facilities, or some could be just passive, just passing data. So star is useful to connect the full function to reduced function. You may have reduced function at the edges, and a star could be full function. But if it's mesh topology, then all of them are full. And we discussed earlier that you can combine mesh and star to make it more scalable. Then the network component for connectivity and routing within a IoT is similar to the previous discussion. And this is the very popular discussion for these routing protocols. Okay? And you can have, it's exactly the same thing that we discussed in the network layer. Okay? Now, only thing is you can think that, okay, the transport components for end-to-end communication provides a flow and a congestion control mechanism. Okay? We did not discuss these things because that time it was not very important, but now it comes to surface that, okay, for MIoT, okay, we will having both the environment with a low power environment, and UDP is always there. At the same time, if that is possible to do this flow and congestion, then that control also, just like regular wireless and network would do that. Okay. Middleware, okay. I told I will be giving some little bit stress on the middleware layer because we didn't discuss in particular what is the middleware layer within MIoT. So middleware is basically a software layer between network communication and operating systems and applications. Okay. Now this layer is sometimes kind of a computing algorithms in a software simulation ways. That is, this middleware layer allows IoT applications. It is more towards application side, okay? Application for heterogeneous objects that is to be developed without needing underlying hardware platforms. So we don't need hardware platform, though the nature of job is kind of as you compute with the hardware. So that is actually fulfilled using a software layer, writing simulation like for that. Then middleware service components can be classified as a functional and non-functional. Okay? The functional component include resource discovery and management, data, event, and code management. So what is saying that, okay, when you talk about implementing functional middleware component, you don't have to use hardware, but all those algorithms kind of take the data, do certain things as we do in computing, doing simple manipulation using software, okay, and apply to scenarios such as discover resources, which are the other agents available over there, then how to manage data, okay, how to manage code. So typically these are all MATLAB-like stuff you can do even using software. Examples of a non-functional requirement is scalability, timelines, so that which you handle like using two types of as we discussed that you have a star and mesh network layer, but then it has to supported by some tools or software. Okay? Then timelinesness, putting timestamps, and making sure that the communication happens, acknowledgement happens, those kind of things also, they belong to non-functional requirements, and including even security services. Okay? So in summary, the middleware layer is a software layer try to fill the gap that you don't need to have a hardware, but still you can achieve a lot of management functionalities. And this is the more important thing that we'll be going to discuss soon. Now, typically, this layer serves as the processing layer or computational layer in traditional IoTs. It has hardware components such as a microcontroller, FPGA, system on chip, and also software, real-time operating components like TinyOS, Contiki, and so on. So for multimedia IoT, there's a third software component is included that's called data analytics. Okay. Now there could be other computational component just to include cloud platform with the servers and some smart object, okay, or could be intermediate nodes also, but typically we use the cloud for processing the data for real-time computation if the operation speed is not compromised too much. So we'll look into how this architecture is taken care of. Application layer again, the same thing using co-op. Okay. Now, this is a summary actually what we discussed last several slides is the summary of the tables, the summarizing whole thing. Okay, so identification layer, we talk about that, EPC or IP, IP numbers, okay, IP addresses. Then physical object layer, we discussed about scalar or multiple, it could be multimedia objects too, both single and multiple modalities. And everything is the same, repeating, basically summarizing here, except this layer. So this is the layer is new. All of them are just there before. We just try to review it quickly. But this is except the middleware layer. And sometimes it's there, some not there. But we are going to talk about this particular layer. Okay, that's actually that layer. So if you notice, you start with the identification layer, physical object layer, communication layer, then middleware layer. Remember that? We did all those things from here to here, middleware. And application layer is there also, you'll see. So this is what we are trying to fill the gap. So you have got 4 stages here, application layer here, the rest of them here, all these things is actually for the big data processing or multimodal big data architecture for IoT. Our purpose is actually to process the data analytics for multimodal inputs. Yeah, we cannot go and come back to this thing while we discuss each of the areas. Now, multimodal computing layer is a layer to perform data integration. First is a summary, then we go back. Okay, so this architecture, okay, is composed of 4 functional units. Okay, 4 functional units. 1, 2, 3, and 4. Okay, what are they? Data centralized unit, multimodal data aggregation unit, multimodal data divide and conquer computation unit, and fusion and decision making unit, 4 of them. We'll take each of them and see how they coordinate with each other or what happens in each case. First to take the data centralized unit. Let's go to the picture and take a good look at it. Can you see this thing? Can you see well? I can see. I don't know. They're so small because I have a small screen here. That's why I'm not able to see that. Okay. Now, you see here that each object 1 object 2, object 3. This is multimodal, this is single modality like image, this is single modality, scalar. So that's what we discussed earlier, right? The 3 categories are there, okay? And maybe repeating similar instances later. And there's a data bus over there. It takes its input from middleware layer, and these are the type of objects we are getting, and that has to be, this data has to be centralized. So let's see what happens here and how much data is processed for what. This is the one, right? The data centralized unit process raw data from various objects. We saw 3 different kind of objects with their own identity. They're unique. And these objects can be scalar, multimedia objects, and multimedia, both single modality and multiple modalities. Then it performs the data integration, data cleaning, data redundancy, elimination. So essentially when you get data, raw data, it comes with a lot of sometimes garbages, additional data of no necessity. You don't want to take them up because they will unnecessarily waste your computation. So you have to identify them and eliminate them. Data cleaning, same thing. Sometimes you got a lot of zeros, a lot of unnecessary ones. You have to clean those things. Okay? So data integration processes, you combine those different data from different objects and cleaning them. What else? You also combine the object data with their unique identity. Since you know that each object has an identity, you can say, okay, this is the data from this unit and so on. For scalar object data or multimedia object with a single modality, no data separation is performed. But, okay, no data separation is performed before combination of unique identity. So that means you first find identity, then you combine. For multimedia object with more than one modality, the 3rd category you saw there, data will be pre-processed. There is no pre-processing, you have to pre-processed. I mean, what happened in pre-processing? You arrange according to the modalities, what do you call that? Multiple modalities, 2 or 3. So accordingly, basically, you try to arrange them before, again, identify them. So basically, first to give identity, then find who are the models and modalities having 2 objects or 3 objects, those kind of things. After the raw data pre-processing is, what is pre-processing actually? It's arrangement, organization of that. The pre-processed data is passed to the next level called multimodal data aggregation unit, that is coming here. So let's take a look at it, and this is multiple data aggregation unit. What you have, this is aggregation data blocks. Okay, aggregated data block. This is multimodal partition data blocks. You have single and scalar and single modality data. That was actually saying that you had to put them together, but before putting together, you have to tag them. Then this is actually similar things, but only for the modalities data aggregation. Then let's try to see what is happening here. Now in multimodal data aggregation unit, what happens? Now there's a need to aggregate and organize the data into proper format for further processing. How? For scalar objects or multimedia objects with a single modality, as you saw that the left side, the blue box, the first aggregation algorithm arranges the data into equal sized aggregation data blocks. Basically, they divide that into blocks, and that helps them for big data analytics. Then multimodal data aggregates the data of the same object source based on its identity and modalities, finding similar modalities together. This unit can be operated in 2 modes, offline or real time. If it's offline, then you have to store that data. Okay? Otherwise, you will pass that to the next level called multimodal divide and conquer. Okay? Now, in multimodal divide and conquer computation unit, which is a, let's go back and see that. Right. This is the one, right? So there's some similarity over there. We can go and see what's going on here. And this should have that storage already there. Storage is for those things that are non-real time data. Right. Now this unit contains, I think pictures are given next slide, but let's see what it's talking about. This unit contains a divide and conquer subsystem with their own computational servers. Each block, they have their own servers to process the data of each modality in parallel. Okay? Usage of the specific divide and conquer subsystem depends on the modality. So that means computation could be different from different one, but they're in parallel. Each subsystem aims to extract the target features. So essentially, each blue box there, they're actually trying to extract the target features. What is target features? Depending on the object. Visual features, image data for scalar and singular, text features for text data, audio features for audio data, and so on. And for this multi-modal things, you go for audio and visual for the video. So this is what happened actually. Okay? That block you see, you get the aggregator block from the bottom level, that level below that, and try to divide the blocks. But you don't know block size. Okay? So you keep doing it until you achieve the threshold, as long as you reach the threshold. So that's why you divide and go back, divide and go back. Okay? Then once you have achieved that, the block, optimal block, then you call target feature extraction function. Okay? And then you go for conquer function. So divide, then do feature extraction, then call conquer. We'll see what's going on in conquer. So division of block recursively, see, until the block size reaches a set threshold. So what is the threshold? You can define for different applications and call it. And you be in this process, then you can find the parameters that to basically say your thresholding is to be loose or threshold is to be tightened. Then target feature extraction function is called, okay, to extract the local features. Then here's the example actually given here, okay, how divide conquer mechanism is done with the scalar or singular modality, and similarly you have also another for the multiple modalities. In say visual features like a color, texture, even that could be texture actually is coarse or fine, directivity, contrast, shape, all these things coming into texture. So color and texture for visual. For audio features, how to extract features? To generate basically audio features is based on a fast Fourier transform, we call the short time fast Fourier transform, zero crossing rate, linear prediction coding. They are all standard techniques in signal processing or otherwise. Volume standard deviation. Okay? So some of the techniques, they can be used for audio, extracting audio features. For video features, for more multimodal things, you get motion feature, motion quality, for direction motion is going up or down, horizontal or vertical, then magnitude histogram, optical flow. So you don't have to remember, but at least you know that's what's going on, so that if there's chance come for you to implement things in research, then they're all handy, but at least get an idea what is going on there. These features are extracted from sub-blocks during divide and conquer mechanism. The second one, this one actually. Yeah, this part. Now go to conquer, the bottom one. So what happens in the conquer function combines and process the features in the reverse order. First you get the features, okay, combine that, then once you have those features, you combine the reverse order. So if something coming one way, you pick it, then go for the reverse order. Okay. Now, when you go reverse order, you go just by taking the two neighbors, then move upwards. If you are coming from bottom, top to bottom, and this time go from bottom to top. And what you do, you still go for the features. So what is the, do you understand what is going on? You typically take two blocks, find feature, next two blocks, find feature, and you get some feature, local features. Once you have that, again now go back, reverse order. So by that, we can shuffling and try to get the best out of all those divide and conquer strategies. Now, at the same time, the block size, the threshold also is important. Okay, and based on experience or based on what is going on around there, you can find this threshold is good enough for me or not. Okay. For each input aggregated data block, from bottom up after this, after the threshold, the final feature block, which contains the local features, is the result. Okay. Oops. Right. So this is essentially is going on. Okay. You partition data block, you part data separations, then you basically apply divide and conquer functions, and in parallel. See. Then after that, all the feature results is passed to the next unit. What is next unit? Fusion unit. Okay. Fusion and something unit. Okay. Fusion and decision making unit, the last unit before you send to the application layer. In fusion and decision making unit, which is the final stage of computation layer, it has feature storage unit, decision making server, and infrastructure for communication. Okay. The servers supported by various algorithms like organize, store, transmit. That's exactly what you need to do. But it's saying that you do this thing based on certain algorithms. So here research is an algorithm that is that you design, if from better, then that is a good research. Okay. The decision-making servers use smart algorithms to make decisions in efficient manner. Same thing is emphasizing that. So after decision has been made, then this fusion decision making unit gives desired output so that any application can use it in real time or offline. Okay. So the final process is, did I miss a figure? No. Okay. Now, so multimodal feature fusion decision making subsystem, FDMU, let's see what is inside that. It has decision level fusion and decision making fusion. Next is feature level fusion. Fusion means join, put together, right? So feature level fusion and decision making. That difference, I think that's the picture next to explain that. See. In this case, the first one, you are trying to make a decision level, this is decision level fusion and decision making. So you first make local decision, then you put them together. Okay? Decision making. That's then the output. Whereas here you do feature level fusion, then decision making. See, this is what is this? Is final fusion module here. Okay, this is final module here. Okay. Now, this is your feature block. So what is difference? Modality 1, modality 2, you are getting D1, D2. They look same, right? No, something is wrong. No, wait a minute. There's something wrong. There should be two different type actually. Yeah, there's something, maybe the picture has been swapped or something there. There are two different In one case, you are aggregating the fusion first and decision. Other one is the decision then fusion, get the final result. I'm trying to figure out what has happened. Yeah, it should not be a different, it should be different one. If you have a feature level fusion, was I look at that this morning, they are okay, maybe something. So, but what's the final presentation? I'll change those things there. Okay. So this is certainly going to change. Feature blocks. You have final decision fusion models. Yeah, the same thing. It should be different. Okay, because see this, they are different. Feature level fusion and decision making. Decision level fusion and decision making. Okay, I'll check that later. Then decision level fusion, again the target, I think you can get an idea what's going on from description actually. Okay, here. The target analysis first provide local decision D1 to Dn, which is basically the left one is correct, based on the individual modality feature blocks. Features 1, 2, 3, all those up to n. And local decisions are then combined. Okay, local decisions are combined using final decision fusion module to make a fused decision vector and analyze. Now, yeah, let's go back. Yeah. So there are n modalities. They are basically coming to decision module. Okay. Then it is fused here before final decision. The second one is decision level fusion 2 by 2. Wait a minute. Yeah, the second one is this one, second one, right? There's a feature level fusion. What happens in the feature level fusion and decision making? The feature blocks are first combined. Decision was taken individually earlier, but now that will combine first. Okay, so which means we should get here, we should get a combination here instead of being separately done. Okay, this one, right? This is the one. Okay, in feature level fusion and decision making, the feature blocks are first combined. Okay, and then sent as input to the feature fusion module. So feature fusion module is a module that is after the second block, which merges the set of features blocks from different modality before the decision making. Okay, and they have their own advantage, disadvantage. The advantage is it can utilize the correlation between the multiple feature blocks from different modality at an early stage, which helps the better decision making. And that's intuitively correct, because if you have the features early, then try to put together, you may get a more elaborate, rich features, and probably you can get heavy weightage features to come out. Okay, and disadvantage is kind of synchronization is hard. You need more computation for that, and it's because the features from the different one closely coupled, and the first one is the representation. Representation means suppose you want to combine two modality, and one modality is represented in machine learning, second one is in deep learning. How can you combine that? So that's the challenge. That is pretty much, I guess. So we define multimodal examples and data for IoT, except that error in the picture, I will fix it in the final one. Briefly introduce multimodal computation model and deep learning. We also examine core challenges of deep model machine learning, then MIoT architecture, then analyzing the both type of MIoT data processing structure. Yeah. No, not much example is there. They have been kind of proposed, and I don't have any example for those things now with me. Okay. These are the architectures always the ideas, and one can, if you want to do research in that area, essentially you will be implementing the ideas. You can augment your own ideas, okay, and it could be implemented, but at least I did not see them in the literature, or because it could be trivial. They don't publish it. If something trivial, don't publish it, because all they are doing is getting the modalities and converting it into small blocks, do the feature extraction, and process it either front end or back end. Okay, the only challenge that mentioned that, okay, if you are combining or fusion, we call fusion. For fusion, they need to ensure that the representation has to same. The representation are different, then fusion is not possible, or a wrong results. So it's not that difficult to do. Okay, so that's maybe the reason it could not be publishable. The idea is pretty low hanging. Yeah, when actually that is definite, that's a common thing. There's no scenario, this is the way it is. That's the way is all those, we saw that multimedia, multimodal is something for processing multimedia applications. Now, when you do multimedia application called MIoT, or multimedia IoT, it shows there are 6, 7 layers are there. And most of the layers are common. After middleware and before application, everything is common. Only that layer is unique. Okay. Now, the question comes, what one can do? You have got, earlier it was all single objective, single modality. Now you have got a lot of single modality, scalar, and also you have a multiple modality. Now, when a single modality, multimodality coming, we are getting many sources of input, and these inputs are nothing but objects. We want it because as you saw that plane in which you different pictures, or sometimes word, sometimes sound, you combine all these modalities, then take a decision. Okay, why decision? Otherwise you cannot take decision. So they come with representations until the computational unit. Now the question is, how do I go to the application layer? Unless I do a proper computation, take the feature-rich answer for the application layer. Application layer looks for the features so that they can use it. And we are coming with many features, and we know they are connected and don't want to separate them. So intelligently, we are trying to put those features together, and that's why they divide and conquer. They have to divide and conquer because they can't process everything together. They put them into single chunks, okay? Then once that they divide and they try to get feature, is after all this is coming from a same set of data, same representations possibly, or similar representations. So they try to collect similar representation, make divide and conquer rules, and check it, both forward and backward. Even if you do forward and backward, the noise will go, but what remains is the absolute solid features. And that feature is carried away and from set to set, or block to block, or you can say rather modality to modality. Okay. And if the 3-4 modality is specifying a particular answer, okay, I do not know what is going here, well, you have multiple modality, there are similarity, we did all those things processing there, then now I am getting feature equally drawn from both sides. When they combine it, they confirm that this is the image about. Okay. So that's essentially the background. So it has to be, there's no, this when we can do that, it has to be done. It's a part of the computing process. Yes, this same thing we are doing. This is what we're doing. We are absolutely doing same thing here. So, how much time will it take to boardroom here from here? 2 minutes, huh? Oh, that's okay. Then we can, yeah. Okay, then, so tomorrow we have you heard about large language models, LLM? Huh? No, I'm not asking whether they heard about it or not. Okay, because tomorrow you're going to, there is a first lecture possible go for the large language model for IoT. Okay, that's a brand new area, but large language models are typically used for other purposes. Okay, now we are attempting to use it for the IoTs, but we start with the standard large language models because tomorrow my graduate student will be talk about it. So I'm giving a little preamble so that when she talks, you know what she's talking here, there. So typically, the large language models you have heard about chatbot. So those things, they're all large language models for translation. They're very powerful. They contain almost all the features in the world, kind of thing. So you just throw a stone, something will come out. Okay, and you can write nice letters, professional letters using chatbot. Okay, 4, 5, all versions are coming, and it's becoming better and better. But tremendous amount of computation requirement, lot of requirement. So obviously, you cannot use for IoT. IoT is very weak in the computing resources. But sometimes I would get things confused as if you think, well, if I have ChatGPT somehow supported, I can get it. There are some few short learning, zero short learning that's there, how they're using different things. But we started to do, assuming that we have computation and my IoT environment, I should be able to get good result. We'll get it. But one hope is, in IoT, we always go for domain, small domain. IoT for this, IoT for that. So our data range is not too much. We're not expect to look at billions and trillions amount of data. We might looking at maybe 100,000, 200,000 kind of data is enough. For me, this room is a world. For others, this whole campus is a world. So dependent application. So we are trying to find out, trying to understand, explore whether we can use ChatGPT kind of framework for IoTs and will succeed. What is the bigger challenge in IoTs? What is the bigger challenge in IoTs? Those are the basic challenges from objective point of view. What is your objective? Why we are doing the IoT? What we are doing? Cognitive, making IoTs intelligent. Okay. So when you try to make IoT intelligent, what is intelligent person do? You ask a question, they answer correct answer. You ask a question, they give you correct answer, meaningful answer. That is the smart thing. Is ChatGPT that do that? ChatGPT, most of the time, they give you correct answer, except randomly they give you wrong answer. But they definitely give you correct answer. But can you use ChatGPT for the IoT high level? Perhaps no. Though it makes sense, but feasibility is remote. So we thought if ChatGPT is a concept for us, though we start with using it, but for us it's a concept. ChatGPT for language translation is a good sources, but it's a huge sources. But we are not looking translation. We are looking some questions to be answered where all the answers are there. And if my IoT has a limited domain, And domain is only, suppose I am using image, okay? Not, when I am using, I may not be using other ones. It's another question, how much multimodality will help, we not thought about it actually, okay? But maybe as you go step by step, we'll see there must be a way out. Okay, so first time we're trying to connect the ChatGPT kind of, we call LLM. So maybe we will not call LLM afterwards. We can call it a small language model or a medium language model, who knows? We may not call them language models, we can call it image models, small image models or large image models, we don't know. Research is like that, research is not something somebody has given to you, your recipe, eat it. You just think novel and push yourself. All those are actually the, what we call that, platforms. So the platforms, we discussed the platform chapter already, but still I'm just going to tell you must have confused because I'm always showing Amazon here, okay, Amazon there. So whether I talk about a simple platform or talk about training, so there is just like they have this Reliance stores here, they are stores in the cloud. Okay, you want to do a lot of FPGA computation, your choice is to buy FPGA, put in your lab and do it. And that's the pain in the neck. Okay, expensive, it's difficult to even put them together. Sometimes it's really not possible. But you go to Amazon site, everything is available, real FPGA with the virtual front things. So you go, just program it as if you are using it in your lab. Get everything done. Okay. So similarly, I'm giving an example here. Similarly, Amazon or IBM or Cisco, all those big corporates, they provide tons of simulators, servers, computational facilities, even for IoT analysis, complete data analysis framework up there. So all you have to know how to use it. And also online you can find all those process steps, how to use it. So instead of using independently yourself, because as an individual, when you want to have so many tools, you really cannot afford also. Even if you can afford, who will maintain that? Okay, your life, 10 years will go even just setting the background, setting the framework. So rather use those frameworks and get things done. Okay, so you leverage their effort by paying or whatever, okay, and save your own time, your career also. So that's a good scenario, okay. In the beginning, I was kind of very defiant and kind of trying to use them, so I built my own server network, all these fancy things in my lab. Then I found that it make me tired and keep doing that, and sometimes this is a problem. Then my students are struggling to fix it. That's not worth. Okay, so I'll sign in those things. Yes, I can. Oh, okay, I'll sit down. Okay. Yeah.